Thank you. All right. Yes, welcome everyone to day 2 of Understanding Latency. My name is Björn Ivar. I'm head of research at Domus, and I will be your host this evening or morning or afternoon. So there are a few practical details. So the format for the event is basically a series of 15-minute talks. And then we will have in between each talk, we will have a Q&A session. And for the Q&A, I ask everyone to use the Q&A tool in Zoom. So for attendees, there is a Q&A button that will allow you to ask questions, and all of the panelists will be able to see those Q&A, the questions as they come in. And I mean, it's not impossible to ask questions in the chat, but it's can be hard for us to keep track of them. So if you want to maximize the chances of your question being actually answered, please use the Q&A for that. And also please note that the session is being recorded. So any questions that you ask and the presentations and answers and everything, we'll put that up on YouTube after the event. We had some great talks yesterday. So if you missed those, you can look forward to receiving the YouTube link and check them out as soon as they are uploaded there. So everyone who's registered for the webinar will receive an email with the slides from all the speakers and the YouTube links. So I think that is all of the sort of practical things that we want to get through. We have a really excellent schedule today. I think we're going to hear from not one, not two, but 3 of the major ISPs in the world, and as well as several companies who are pushing the boundaries of low latency technology and really, putting out new technology and improving the state of the internet. So I'm very much looking forward to the talks. Yes, final detail. If all of the presenters who are not presenting can turn off their video and audio while each presentation is ongoing, that would be great. Otherwise, we can also override it for you. So there's no mercy. So with that, let me introduce Jason Livingood from Comcast. He's leading research technology, policy, and standards at Comcast, and they have been doing some really interesting trial work on L4S in the last few months, and I'm looking forward to learning more about that. So please, Jason, the stage is yours.
All right, sounds good. Let me.
I will let you know when we see the slides and everything. Yep, there they are. Everything looks good.
All right, perfect. So thanks, everybody. I'm going to talk to you today about Comcast's low latency networking trials, which have been underway for a little while. Just a high-level view of what the DOCSIS network looks like. We have an aggregate service flow that is provisioned to a customer, and that aggregate service flow indicates the priority of the packets as well as the overall bandwidth. And so it's important, we've been trying to make sure folks understand, particularly policymakers and regulators, that the low latency service flow, the low latency queue, if you will, shares the same overall bandwidth and shares the same best effort priority. So it's very clearly not different priority, not different capacity, which is a common point of confusion. A lot of people really focus on thinking that in order for something to be lower latency, it means it's higher priority, and that's really not the case, especially as we are in a sort of an era of bandwidth abundance, not scarcity, and so it's helpful as a level setting for folks. So we've been trialing on our virtual CMTS platform. So the CMTS is essentially the next hop outside of the home. And we have a platform that we've been working on for several years, and which is really the new part of the network, if you will. About half of our network so far is upgraded to virtual CMTSs, and think of that as like server-based, disaggregated in terms of the functionality versus a very vertically integrated, what we'd call integrated CMTS, with sort of classic line cards and ASICs and those kind of things. So we're on the virtual CMTS platform for this trial, and we've got 4 different cable modems, both Comcast provided, which are our own gateways that run software that we manage, the XB8 and the XB7, or 2 customer owned and managed, which we would call retail devices, an Aris and a Netgear. And the objective there was to try both ones where we control the software as well as ones where it's third party. They can be located anywhere. So because it's using our virtual CMTS platform, we're not limited to, say, one particular city or something along those lines. And, really interestingly, we found an unprecedented level of customer interest. We had thousands of volunteers, which is significantly more than we would typically see for a trial. That gave us a great base of possible candidates to go through and decide, how to get the right mix of speed tiers, devices, geographies, etc. And we proceeded to launch first with employees in July, and then customers in 2 separate waves in August and then in October. All right, so continuing on, the first phase, we did upstream cable modem support, and we're still only doing upstream support for both L4S and NQB. So essentially being able to mark either with the ECN header, in the ECN header, or in the DSCP header, so ECT1 or CE and DSCP 45. I will say there that we did broaden to 40, 45, 46, and 56 because before the IETF had really narrowed down a port assignment for the NQB standard, there were a bunch of providers that, from Xbox to others that were using different numbers. So at least for now, we've been a little bit more expansive in what we've chosen to accept there. We think that'll probably, get fixed over time as people coalesce around whatever standard the IETF releases. We have been getting ECN to work upstream and downstream with no bleaching. I should note, though, that we did find a bit of a bug early on where our test of bleaching was really just an outbound test, so upstream. And then we started noticing early on that it wasn't working downstream. And so we had a bunch of configurations in the network to go ahead and fix. We have so far done manual provisioning of cable modems. That's fine in beta testing and field testing, but doesn't really scale. So a later phase of this, the next phase 2, which we'll be in shortly, will have automated provisioning, which is important for us just to get all of the operations and management tools up to snuff and tested and so on. And we have been able to test end-to-end DSCP 45 marking with one of our network peers. We'll show you that later. And we're in the process of rolling that out across the network. The approach that we've taken with customers is that essentially the first week we ask them to just monitor their usage after they've been given low latency configurations and report anything odd. And then after that, they basically get a weekly assignment, whether that's an Apple network quality test or other kinds of diagnostic latency interload tests, etc., where it might be a FaceTime test while they're running latency generation tools or low latency DNS, so on. So we tried to sort of first give everybody an option for doing weekly activity. So if they're using a Mac, they have a Mac OS type of test to run, or if they're running Windows, they have a test to run. So nobody's sort of sitting idle for a week. But at the same time, we didn't throw 20 things at them. We tried to parse that out over time. And they would then ask to submit survey forms with quantitative results from each of those tests that we've been analyzing. And we've also installed a number of probes from Ripe Atlas, Sam Knows, University of Chicago's Net Microscope, and Cable Labs probes. So that'll be interesting as well as that data continues to come back. At a high level, we haven't noticed any of the classic queue starvation issues that folks were worried about. Things appear to be working as expected so far, but the one thing that we have found is that there's probably a shortcoming in some of the, or I would say a limitation in one of the cable modem configurations that we've been using. And that's affected a really higher bit rate L4S traffic, not lower bit rate L4S or NQB traffic. And we noticed this with some of the FaceTime testing and Apple network responsiveness testing. And essentially, we've got to go and fix that. It's a cable modem setting. So we're kind of waiting through holiday moratoriums and testing different configurations in the lab at the moment. But we'll expect to roll that out, fairly soon. And as I noted, that was really a bandwidth limitation of the low latency queue. So not something that we noticed with things like cloud gaming or other cloud native types of applications that were lower bit rate, but it was sort of, more of the higher bit rate ones. So we think that, while the performance was good in that low latency queue with those higher bit rate applications, they'll get even better. So we continue to iterate, and that's one of the normal things that we would hope to find and sort of smoke out in a beta test or field test. So lots more trial work planned. The first intra-domain DSCP45 packet exchange that we did was in October, and that was with Valve. Obviously, that's a big deal, as is typical for most ISPs. When you can use whatever DSCP marks that you want inside of your network domain, but once that goes over a domain boundary, you typically bleach those things out because people are using different DSCP marks. So this was the first opportunity for us and up here to allow a marking to come across unchanged, which was important and sounds less complicated than it actually was, but we actually got it done, and now we're in the process of making those changes across our peering routers network wide. That'll take a little bit of time just for stability. Those are obviously devices that have to be highly reliable. And I'll skip that one. So we have a platform that we call IMP, a creative acronym for Internet Measurement Platform. Another engineer named platform, which is always fine. But it's basically a network testing agent that is embedded into our cable modem gateways. So those XB devices, XB7 or XB8, that are running the sort of open source software called RDKB. And the advantage of having a test like that is that it basically controls for any of the in-home variables like Wi-Fi and so on by running on that gateway and just testing that access network portion. And what we see so far is basically a 50% reduction in latency and lag, if you will, which is positive. So we'll expect to see more benefit there when we make some further cable modem configuration changes. But positive change so far. With NVIDIA and their cloud-based gaming platform, GeForce Now, which is actually pretty cool, we've been doing a bunch of analysis of that traffic, and we really rely on partners like NVIDIA to give us statistics from their clients, because you can't really observe QoE just as a network operator in the middle. You depend on the application owner to share some of those stats. And that's been really great. So the first thing is you've seen significantly lower jitter, but also consistently lower jitter. So that variability, really disappears for latency. And that's a really positive for a lot of application QoEs. And the other helpful thing here is, this is while we've been throwing, in many cases, load at the connection. So it's not just steady state user gaming with this marking, but also while we're asking them to run an application that generates traffic in the background. So that's actually really positive as well. And, really a cool use case for platforms like GeForce Now that have cloud gaming, and then they've also got a cloud AR platform as well. And one example that we did is, while we're off running, while a customer's off running a latency generation, a load generation tool, which you can see with the white and blue circle there in the sort of upper right-hand corner, that throws sort of variable and bursty traffic at the connection, upstream, and gets traffic back downstream, of course. And in this upstream case, what we notice is in this video, sort of the car is rotating, there's music playing, and as that generation happens, it gets really jerky and sort of buffers and so on. You don't see that on the right when we generate traffic, and it's marked as low latency. So that was really cool, just as a very visual one, because for end users, it's helpful to see that, not just some chart of esoteric latency numbers. Another platform partner that we've been working with is Valve, which has their Steam platform. So these are games like Counter-Strike and a number of others that are really fun to play. And in this case, we see only a slight difference between idle latency and loaded latency using the LLD queue and the low latency rail forest queue, if you will. And so, that was another really positive case for us to see. And I think shows again that a lot of those sort of cloud, native games and so on, those platforms are seeing a really nice benefit. So here's the Apple Network Quality Test, and this is the example of when we started to say, maybe something's a little bit off with our cable modem configuration, because when we're seeing a higher bit rate, we're not seeing the benefit that we wanted. And so we didn't see, in some cases, a huge difference, although on the right-hand side, you can see that we did have users see substantial differences, 76 RPMs to, almost 1,000, or 250 to, 967 and so on. But we thought we would see a little bit larger one. And this was, similar to the sort of qualitative differences that we saw with things like FaceTime. And so, that was the lead for us to really dive into the cable modem configuration files, along with, Greg White at Cable Labs, who's been a great partner, and, working with our Apple partners to kind of dive into that. So we expect some changes there that should improve the higher bit rate things. In terms of network probes, one of them was at University of Chicago and their network microscope platform, net microscope, excuse me. And so, they've right now just been looking at overall latency under load. So think of that as sort of creating a baseline of data as the control. And they are now working on, and I'm having a conversation soon with Nick Feimster from that team about how to implement DSCP or ECN marking, so that they can basically run the equivalent latency under load test with low latency marking. And so that'll be really interesting to see what the comparison is once that is there. Similarly, the SamNose platform, we have a bunch of those probes out there. I think they're all white box 9s. And they've implemented sort of their own version of the Apple Network Quality Test. So again, similar to the University of Chicago Net Microscope platform, the SamNose platform right now is just using the classic queue. And so we can see some of the responsiveness numbers that are here. And this will be a great base of statistics to then compare against it once they get ECN or DSCP marking, probably DSCP marking implemented. So that'll be another interesting platform. In terms of next steps, we anticipate testing will continue through at least March, but that's sort of our target, is to try to wrap up by the end of the first quarter. As I noted, we do expect an iteration of our cable modem config, and that'll come soon. The other thing that we'll be adding is downstream dual queue. So far we've only been testing upstream. And we, of course, sort of field validated a beta version of that code in October, so we'll be doing that. We're also be implementing automated provisioning, so we can test a whole variety of different speed tiers with different upstream and downstream speed tiers, just to test and make sure they work, for a whole variety of, customer types. And then any other operations and management systems that we need to deploy and monitor it, for something that's at scale. Of course, we're still soliciting any tests for end users and applications. Happy to partner with you if you want to reach out. And, the plan for us is, as we move into next year, to scale this out operationally to millions of users. So we do anticipate pushing this out. And I should say one other thing up in the cable modem configuration that I think I neglected to mention earlier. our cable modem gateways have Wi-Fi built in, and so we actually are doing downstream Wi-Fi marking, and that'll be another key part of this as well, to compare Wi-Fi using different WMM marks versus just B default B default BE traffic levels for WMM. So anyway, preparing to scale up. Very excited about that for next year, and I'll stop now and take any questions that folks have.
Great. Thank you very much, Jason. Did you find the Q&A tool? I can read the
Yes, I see
questions
them
to you,
now.
or might be easier if you read them yourself. I'm not sure.
Yep. So one question here is about whether we're planning to use proactive grant service, PGS, within the current low latency DOCSIS trials. At the moment, we are not planning to use PGS as part of that. However, we have a separate research initiative into potentially turning PGS on in our full duplex DOCSIS network. And for those that don't know, proactive grant service is a way to basically lower the time that it takes for the request grant cycle in DOCSIS in that link layer, if you will. And PGS does introduce some inefficiency or decreased efficiency in bandwidth usage. And so that's why in the much more bandwidth abundant full duplex, sort of full symmetric gigabit network that might be a possibility. So we're looking at it for some of our network next year, but it's not coupled with our low latency trials at the moment, though it of course could help further lower latency. So it's a TBD future to test. And then another question here is for the NVIDIA GeForce Now stress tests. Oops, where'd that go? Whether the background traffic was low latency or classic. The background traffic that we generated was using the classic queue, which of course for us used the overall same amount of bandwidth and priority. That was the only application using the low latency queue. So that's where we are at the moment. Of course, we don't really control what else the end users are doing. So if they're doing other things, that might be marked as low latency, it's hard to know about that. But that may introduce another interesting, case of also using that traffic generator to mark some low latency tests, which is easy to do. So the next is, were the gaming end devices connected by Wi-Fi? There are two cases, and we asked users to record that in their trials. We have both of those things. So both users on Wi-Fi and users on Ethernet. When they recorded their test results, they were asked to flag that. And so, for example, when you see the NVIDIA results, that's all of those test cases of Ethernet and Wi-Fi. We'll record in our data set the difference between the two. And obviously, Ethernet is superior from a latency standpoint, and there's a lot of variability in the Wi-Fi network. On the other hand, when packets come down into the cable modem gateway, if it's our gateway that has an integrated access point, if it's marked for the low latency queue, it's going to be put into ACVI, so the AC video queue in the Wi-Fi domain. All right. So another person related to that asked why we will try different WMM ACs. Basically, there's a lot of measurement data out there, and it's been shared previously that putting latency sensitive traffic into a different WMM queue, if you will make that traffic be more responsive. And so, we're working to validate whether that's the case. And in the example of our gateways versus customers and using their own Wi-Fi networks, you'll have a test case of, customers being put in different WMM ACs versus not, just being in the default BE AC. So, that'll be an interesting comparison, but, I anticipate the data will prove out to what we've seen in the lab and what other people have reported in, research tests that different WMMs are helpful in the Wi-Fi domain.
All right. Thank you very much, Jason. There are more questions, but I'm afraid we're out of time for the Q&A. It's possible to answer them like to type answers. So if you do have
we'll try to
time,
do so.
you can
Yep.
do so. All right.
Thanks.
Thank you very much. So our next speaker is Stuart Cheshire from Apple. And he's been working on fighting latency for a very long time. And will be telling us about communicating about this issue and with some emphasis on the L4S standard. So please, Stuart, take the stage. We can see your slides already. You are muted at the moment.
All right. Are you hearing me now?
Yes, loud and clear.
Excellent. My name's Stuart Cheshire, and I'm a distinguished engineer at Apple. Good morning, good afternoon, good evening, wherever you are in the world. When I was preparing for this, I was originally going to talk about technical details, like I have many times before, but I realized that if you're attending this webinar, you probably know a lot about latency already. So what I realized is, I think it's more helpful to talk about suggestions and advice for how we can communicate these issues to other people. So I'm going to talk a little bit about some suggested language. I'm going to talk about use cases we should describe. And I'll talk about some other key points that we can communicate to people. So the first point is to be very careful about the words we use. Anytime you're writing or talking about networking and you find yourself using words like fast or speed, pause and ask yourself if that's really the right word. Do a search in your document or your presentation for fast and speed. Sometimes those are the right words, but 90% of the time, it's more informative to say things like capacity, bandwidth, or throughput. Imagine a journalist writing about a new Wi-Fi 6 access point and saying that Wi-Fi 6 is faster than Wi-Fi 5, but the latency is higher. They can then write a whole article going into technical details, but the average reader takes away the headline, which is Wi-Fi 6 is faster, but something technical about latency I don't really understand. And it's very interesting, but when it comes to their buying decision, they're probably going to come back to, yeah, I still want the fastest network. And we're not giving them good guidance there, because a network with high latency is not faster, but some qualifier. It's not. It's slower. It's slower in the sense that people understand that word, that they will spend more time staring at little spinny wheels on their computer screen waiting for things to get done. So we can say Wi-Fi 6 has higher capacity, but overall it's slower, because when people make their buying decisions, and that drives the whole industry, they're going to want the fastest thing. And that's what we want for them. That's why we're doing this work, is to make the network faster. So let's stop using the word fast and speed as synonyms for throughput and capacity. We can't stop other people from making that mistake of conflating those terms, but at least we can be disciplined ourselves to avoid making the same mistake and being part of reinforcing that misunderstanding. When we're having technical discussions, another word I've found is very unhelpful is congestion control. When you talk about that, sometimes people will tell you congestion doesn't happen anymore on the internet, and then they stop listening to you. And it's too hard to explain the nuance that in the context of transport protocols, the term congestion control has a very specific technical meaning, kind of like the way subatomic physicists talk about spin and color. Those words don't correspond to our human understanding of those words. Quarks don't literally have a color. It's a word used by analogy. So I find it's much more informative to use terms like this: rate management, rate adaptation, because that's what congestion control is. When network engineers talk about congestion control, they mean the algorithm that decides how fast the sender should send packets. And maybe we shouldn't have called it congestion control in the start. because that leads people astray. Anytime you're talking to someone who's building their own protocol over UDP, if you ask them what congestion control they use, half the time they smugly tell you that they don't need congestion control for their application. But if you ask them the same question a different way, if you ask them what rate management algorithm they use, they're more likely to pause and think. It's pretty clear to all but the most stupid programmer that they'll need some algorithm to decide what rate to send out their UDP packets. They're not just going to write a loop that spits out packets as fast as the CPU can go. And now you've got them started on the path of actually thinking about what it means to design a network protocol. The third word we have to be careful about is latency. Used by itself, by default, without any qualifiers, latency usually means idle latency. It means doing a ping on an idle network and seeing the best case round trip time. So when we say latency, even fairly experienced networking engineers think, oh, you mean the ping command, and you have to do that when the network's idle. And as Bjorn talked about yesterday, we've got the propagation delay of signals on the internet under good conditions within a factor of 2 of the speed of light. So idle latency, we've done a really good job on. But when you throw queuing delay in, you can multiply that by 100. So a lot of people talk about latency under load, which is a technically good term. But when we're talking to executives and decision makers in companies, that phrase conjures up the wrong mental image. When we talk about load, it implies some abnormal overload condition. And people think that isn't worth worrying about. Because if it's an abnormal error condition, it should never really happen anyway, or it should be very rare. And if the network is under some kind of denial of service attack, then it's reasonable. We wouldn't expect it to work well. So the fact that latency under load is poor is something that is not surprising to a lot of people. They kind of expect that. And that's the mistake. They shouldn't expect that. So that's why we came up with the term working latency. Because any time you're doing any bulk transfer on your computer, you're downloading an application, you're uploading a video to YouTube or social media, you are using the network at capacity. And that's what you want to do. You want the file transfer to go as fast as possible. So one iPhone sending one video to a friend using iMessage should load your network to 100%. And if it doesn't, file a bug report, because we should do better. So being unload is not a weird failure mode. It is the desired condition when you're using it normally. So using the term working latency conveys the right message that these are normal conditions. This is not an error that we can ignore. This is day-to-day operation of the network, as it should be under load when you're using it, and it should behave well in those conditions. My next part of advice is what use cases we talk about. It's very, very common whenever you read some article about latency, they talk about gaming and video conferencing as the real-time applications that are delay sensitive and need low latency. And that's true. They benefit from low latency, but they're not the only ones. Everything we do on the computer is more pleasant and more productive if it happens faster. When we have traffic classes and priorities, and you can read lots of advice on Reddit about how to tune your settings. We've been working on this for 20 years, and the fact that we're still struggling is a sign that it doesn't really work. Somebody has to decide what traffic is privileged. Who decides that? The OS vendor, the application writer, the user, the network operator. When they've decided, how does the network know which traffic is privileged or not? Is it based on port numbers? Is it based on deep packet inspection? Encryption protects against that. And whatever mechanism the network uses to know, what stops applications cheating and claiming to be the highest priority because they want the best performance for themselves? The most important issue here is it doesn't solve the real problem. Networks like the old ISDN network used to run at a fixed 64 kilobits per second. Applications knew to only send data at 64 kilobits per second. But the internet supports a vast range of speeds, from kilobits all the way up to gigabits and beyond. The only way an application can find out how much capacity it has is to try. And in today's internet, the act of trying risks building up a queue that creates unacceptable delay. No amount of traffic classes or priorities can protect an application from the damaging effects of its own traffic. The other risk of citing video conferencing and gaming as the main users of low latency is that we risk it being ignored by anybody who doesn't care about video conferencing and gaming. A lot of business executives probably don't have time to play games, and we don't want them thinking, well, I'm not a gamer, I don't care. There's also a risk of this feature being marketed as a special mode that you have to activate on your home gateway before you start a video conference or game. That's not what we want. We want consistent low latency for all traffic all the time. We don't want it to be a special feature that you activate for special occasions. We all know the cliche, when everything is a priority, nothing is. With traffic priorities, there can't be winners unless there are also losers, because if they're all the top priority, that's the same as them all being the lowest priority. They're all equal. And that's because bandwidth management involves allocation of a finite resource. What we're doing here is improving user experience for all traffic, not just a privileged minority. How is that possible? Well, the reason is that delay management is not a zero-sum game like capacity management. Capacity is a fixed resource that's apportioned between flows. For one flow to get more, some other flow gets less. But delay is not like that. There isn't some predetermined queuing delay budget that must be met, so that if we reduce queuing delay for one flow, we're required to increase queuing delay for some other flow. And this is counter to our own personal experience, waiting at airports, at the post office, at the DMV, sitting in a car in rush hour traffic. But that's because computer networks work differently from our own personal experience. For a start, network packets can be rapidly created, duplicated. Packets can be duplicated, scheduled, and destroyed in a way that has no parallel in normal human life. We need to be very careful about applying human intuition to systems that don't work at all like the way normal human life works. Another key point, we need to explain to people that network traffic shapers can't actually do a lot to shape traffic. The only thing that control packet rate coming into a network is the end device generating those packets. If those packets arrive faster than the bottleneck link can carry them, a queue builds up. The only way the queue buildup can be averted is by persuading the sender to slow down. The only way to persuade the sender that it's sending too fast is either to discard some packets, which is destructive, or more recently, to mark some of the packets with congestion experienced, if the sender supports that. Either way, it's a partnership between the network and the end devices cooperating to make this work. Anyone who thinks they can shape traffic or manage network solely in the network without the end devices playing along is not understanding what they're doing. And finally, our work over the last couple of years is paying off. We are starting to now see more end user tools that let users measure working latency. Ookla has added it to their well-known speed test. Cloudflare has too. And we have worked at the IETF with an effort led by Professor Will Hawkins from Cincinnati on defining a standardized methodology for how we replicate representative working conditions on a user's network and then measure the responsiveness under those conditions. That internet draft is currently nearing completion. So we really ask people to take a look at that, because now is the time for comments before that finally gets published as an RFC. We currently have 3 open source implementations that I'm aware of this standardized IETF network responsiveness metric. We have the network quality tool built into macOS. and Professor William Hawkins has been leading work through the GitHub Network Quality Open Source project. And he mentioned yesterday about the weekly meetings on Thursdays that everybody is welcome to join. So with that, I would love to get feedback and suggestions from other people who have ideas to communicate effectively about working latency.
All right, thank you very much, Stuart. There are a couple questions in the Q&A tool. So if you pop that open, you can. I find it easier if you read the questions yourself.
I have got it here.
Sometimes the questions include things I don't understand. So.
All right, I will answer these as quickly as I can. What are my thoughts on quality of service? I lump quality of service in with priorities and traffic classes. It's all of quality of service and differentiated services, DSCP in the IETF, is predicated on the idea, it's right there in the name, differentiated services. Different traffic gets different service. And we are really pushing for a much simplified model, which is ideally one class of service, but realistically probably two. We want low latency for almost everything. Web browsing, video conferencing, all of the things we've talked about. We also want a bulk traffic class for big downloads. But I'm talking about application downloads, OS downloads. For most of our day-to-day traffic, I hope that becomes low latency traffic, because browsing a website is not hundreds of megabytes of data. It doesn't need gigabits of throughput. What it does need is low round trip delay. So I think two classes of service is the right number. Next question is, rate seems to imply throughput. I agree, rate does imply throughput, so I'm not sure. If that question was related to my comments about rate management, I think that's okay. That's what I meant. A sender has to regulate the rate it's sending packets, and ideally it wants to regulate the rate so it doesn't build up a queue. So that's the interplay of those two things. Next question, do we split the latency between WAN and LAN and analyze them individually?
That question's for Jason, I think. But the other ones are, I think, for you.
Oh, it does say at Jason. Yes. I will give a quick answer about that. I think there's a mistake in this question. It says L4S is only on the LAN side, and that's not true. L4S is end-to-end. Where it's critical is L4S packet marking at the bottleneck. The bottleneck might be a Wi-Fi access point. It might be your cable modem in the upstream direction. It might be somewhere else in the internet. So L4S is end-to-end. For most people today, the bottleneck is close to their home, but doesn't have to be. Next comment, I love the term working latency, but I find latency is not generally understood. Suggestion is working delay or working responsiveness. Yes, great suggestion. And in fact, that's why the internet draft is called a responsiveness measurement, not the latency measurement. And we use the term responsiveness because people like metrics where more is better, bigger numbers are better. So we count responsiveness in round trips per minute where more is better, whereas latency is typically in milliseconds, which is a little bit of an abstract concept. How long is a millisecond? Well, too small to notice, who cares? So yes, responsiveness is a really good term. And I think we're more or less out of time. We've got two more questions here. How do you see capacity and traffic using scalable congestion control algorithms? I think that's entirely the point of L4S. L4S is low latency, low loss, scalable throughput, and people forget the S part on the end. But a scalable congestion controller becomes more important at high data rates. And what it means in this context, when people talk about scalable congestion control, classic TCP, Reno, and Cubic have a property that the throughput is proportional to the square root of the packet loss rate. And What that means is that as the throughput goes up, the packet loss rate has to go down with the square of the rate you're trying to achieve. And that means that even small packet loss rates become significant. A scalable congestion controller like L4S, the relationship is 1 over P, not 1 over square root of P. And that's what the scalability refers to in L4S. And then I think the last one, if we came to the conclusion that prioritization is going to be abused, defeats the purpose. In your opinion, what dimensions do we have to determine? Okay, so this, I think, is a question about fairness, and good question to end on. FQ used to stand for fair queuing. We had weighted fair queuing and algorithms like that. And the acronym got kind of retroactively renamed to be flow queuing, because fairness is a slippery concept. What is fair? Is it a fair share of bandwidth per human user, per device, per application, per TCP connection? If it's per connection, it encourages applications to open lots and lots of parallel connections, which can be wasteful. So people have realized that fairness is really tricky. But fortunately, it doesn't matter. The ISDN network ran at a fixed 64 kilobits per second and was very well managed and very fair. And a different community of networking engineers came up with things like Ethernet, which is not fair at all. It's only very loosely fair statistically, but it's really, really fast. So there was a decision to put our engineering resources not into very detailed management schemes to make the network fair, but just to provide enormous throughput, enormous capacity. And when you have a huge abundance of capacity, strict fairness becomes less important. Very rough fairness so that some flows don't get starved is what we need. And we say that because if we agonize too much about trying to provide fairness, that is futile. We will never do that. And we will just waste time trying to do something that is impossible, or at least very, very difficult to do. So putting our resources into abundant capacity and using that effectively is much more fruitful than putting our resources into fairly managing a very constrained low capacity network.
All right.
And I think that's my time. Thank you, Bjorn.
Thank you very much, Stuart. Our next speaker is Gavin Young from Vodafone. He heads Vodafone's Fixed Access Center of Excellence, and we'll be talking about how Vodafone sees the next generation or the third era of broadband. So Gavin, please take the stage.
Okay, thank you.
We can hear you loud and clear, and your slides are now coming up here.
Okay, can you see those?
I can, yes.
Yes, great. Okay, right. Thanks very much, Bjorn. So I want to talk about, as you mentioned, Bjorn, the third era of broadband, and specifically to focus on 3 key industry challenges in this area of responsiveness or latency reduction. So first of all, looking at the broadband market evolution, I think the first era was one of increasing speed, and I'll have to change my terminology given what Stuart's just said. But basically, we were in the era, some of you are old enough to remember when we could only get 500 kilobits broadband or 2 megabits at best. And then we evolved to 10 meg and 100 meg. And that was kind of a mass market proposition around speed, in that every time we stepped up the speed, web page load time decreased, as Bjorn showed yesterday, and the ability to deliver higher quality video improved as we went from standard definition to high definition to 4K Ultra HD. So basically everyone benefited from that, and that set the template for how broadband had been marketed. It was all about speed. My number's bigger than yours, so it must be better. Then came the era of mass video adoption. We heard from Will Penson yesterday that 82% of the internet traffic is video and 25% is live streaming. So that takes not necessarily a higher peak speed, as it were, in your broadband product tier. you don't necessarily need to go to really high speeds to cope with streaming, given what you can deliver with 20-25 meg. Depends on how many points of consumption you've got in the home, of course, but that also coincided with lockdown and more people using video conferencing. So even though video conferencing bandwidth requirements are quite modest, but when you've got a huge amount of people all using that simultaneously, then that generates the need for capacity in the network. So higher speed technologies are extremely useful in that context. And the main benefit there really is you reduce any slowdown in the busy hour in the evening peaks. You reduce that slowdown in throughput there. So that's been the more recent experiences given lockdown and the rise of the over-the-top video streaming. But I think we're now moving into this third era, the era of the more tactile internet, where, as we've heard, responsiveness or lower latency become more important. And I think this starts to become where we think about aggregating pockets of niche demand in different areas. So speed and capacity and reducing busy hour throughput are pretty obvious. That benefits everyone. Low latency, as Stuart just said, low latency actually benefits everyone, but not everyone realizes that. The folks most attuned to this are gamers who are very conscious of their ping time, and they're actually willing to pay for an improved experience. These are the folks who sometimes will spend $500 or $600 on a gaming router, for example. But there are a lot of other niches that would benefit and may be conscious of the need for low latency, whether that's emerging XR, collaboration and gaming opportunities there, or musicians wanting to all work together but remotely located. But reality is, this does improve things, even for the humble web surfing. It benefits everyone, but in terms of messaging and identifying, who's most interested in this, I think it's pockets of niche demand there. But those niches in themselves, you aggregate them, and they all actually care quite passionately. It's a bit like not everyone's a parent, and not everyone's interested in parental controls, but you combine that with a number of other more niche requirements, and so I think we're going from the obvious mass market scenarios to aggregating niches and driving things forward. And so the technologies here, I put it under the label of QoS, but really this is about improvements to scheduling. But that's a lot longer to fit in the box there. And one of the other things that's coincided with this move to this third era is the fact that it's coincidental with the shift from hardware-centric to software-centric networking. So increasing end user peak speeds of products requires different access tail technologies. Increasing capacity can be lifting and shifting boxes or interfaces from 10 gig to 100 gig, or digging up fiber in the road, quite capital intensive. Whereas in the software-centric era of virtualization, SDN control, all this good stuff, service delivery platforms, we get to a point where optimizing scheduling, yes, sometimes that's going to need new equipment, but there's a lot we can do with optimizing configurations on existing equipment, and basically programming the network better. So hopefully, in terms of investment required in the network, we get more bang for buck in terms of moving the dial on quality of experience for customers. So in terms of improving responsiveness, over the last year or so, my team and other colleagues in Vodafone, we've been working on a lot of these technologies and approaches in front of us. We've been trialing and or testing a lot of these. We've been testing Wi-Fi multimedia under different congestion scenarios, fine-tuning AQM parameters in the network, testing low latency DOCSIS, looking at multi-vendor interop, different cable modems, different CMTSs, different chipset vendors. We've also been looking at testing L4S more recently. We've been looking at the new quality of outcome approach that Magnus will talk about tomorrow. We've made extensive use of quality attenuation testing. We've also been looking at some of the network as a platform APIs around quality on demand as well. But obviously, there's a lot of information has come out of those testing and trials, and too much to summarize in a 15-minute slot. So rather than try and pick my favorite and compress it down, I thought I'd stand back from the technical detail and just think, given this foray into different technologies and improving latency, what are the gaps? What are other issues that might be worth thinking about to drive things forward? So I think there are three areas. One is demarcation of latency. One is quantifying the benefit of low latency, and finally proving the benefit of low latency. So let me just explain what I mean by those. So in terms of a problem statement, you may hear a customer saying, well, why is my app laggy? Is it my device? Is it the broadband, the network? Is it my video conferencing or streaming service or whatever application I'm running? And if they do think it's to do with the broadband network, where in that network is the problem? Because customers don't really know the difference between a Wi-Fi problem and a broadband network problem. They use the terms Wi-Fi and broadband interchangeably when they have a problem with their internet, if it's broken or slow or laggy. And so really a demarcation of where the issue is could be useful. So where are we today? Well, enterprise customers have got probes and things, and they can afford to have capabilities like that instantiated in different areas and get a bit of a grip on these things. But for your average consumer broadband user, typically if they do any testing themselves, they're going to revert to a speed test. And there's some examples here. Apologies, so I missed your favorite one. There's obviously a huge amount on the market. And what these tools tend to do, they include latency testing. They do round trip time testing end to end. They can separate upstream and downstream. And they can, as we've just heard from Stuart, they can do working latency testing as well, which is great. But what they don't provide is the demarcation of performance, for example, between the home network, the broadband network, and the wider internet, which can be where the application or content providers' servers are. So that's a limitation. Where we'd ideally like to get to in a perfect world is to have full quality attenuation measurements end to end across the digital supply chain. So that this is the vision, so that every link, every hop, we understand the latency, both upstream and downstream, and we can separate that out into the different components of latency due to geography or distance, as we heard from Cloudflare yesterday, or the serialization delay, clocking packets in and out, or the variable delay that's due to queuing and scheduling and buffering. And if we could get to that point, we'd have this kind of X-ray vision into exactly where the link is, which direction it is, and what the likely root cause is, and we'd be able to be much more focused in responding quickly and focusing resources on addressing that. But that's going to take a while to get there. Even though standards exist on how to do this, it's not fully embedded in all types of equipment for time stamping, etc. So that will take some time, and bolting on co-processing probes, as it were, on the side is also an expensive proposition to do that, on any scale. So where do we start? So a simple demarcation to start with would be helpful. Is the issue the thing that's limiting responsiveness or adding to latency and that degradation in quality? Is that happening in the customer's home, or what fraction in the customer's home versus the broadband network and versus the wider internet? So this is not rocket science. This is very doable. The trouble is there's almost too many options in terms of how you go about this. So some solution considerations, who are the target users? Is it the end customer? Is it the network operator? Is it application developers? Do you go for a standardized approach versus proprietary? And standards are great, but that will take a little bit of time. What's the scaling required? What degree of coverage of customers you're looking to achieve? What's your choice of measurement protocol, STAMP, TWAMP, ICMP, whatever? Is it an on-demand versus a continuous test, active versus passive, customer initiated, where runtime is important, or network operator initiated? If you're using kind of reflector sender type approach, then what are the locations for those? Does this require integration in the customer premises equipment, or can it work with existing CPE? And if you've got a probe capability, is it hardware centric? Is it virtualized, instantiated on demand, or permanently there? Does it involve an app? And then you get into the areas of the measurement granularity and accuracy, the duration of retaining those results, and any techniques you're going to use to aggregate and summarize results. All those will have an impact on storage costs for those results. So lots of dimensions to think about, but certainly it's addressable. So the second challenge, I think, is quantifying the benefits. So problem statements here, for example, if I invest in improving latency in a particular part of the network, will the customer benefit? And this is the typical question I might get from my commercial colleagues. You know, we come along, all the technologies I showed you earlier, and say, oh, guess what, guys, we managed to shave 10 milliseconds off, you know, some latency here. And they say, well, that's nice for you, but so what? You know, will the customer notice any improvement in their application outcomes? Do they care? Would they be prepared to pay for this? And which applications would benefit most? So how can content and application providers understand the network impact of their product as well? And would invoking, you know, quasi in inverted commas there, make an improvement to their customers? Would it make any difference? So back in the speed era, one from the earlier slide, this was quite simple. If you came up with a new product that was a higher speed tier, we're basically investing in the network, improving, you know, the bandwidth capability there. The apps, you know, worked noticeably better, whether it's web page load time or your video looked better, and the customer could verify that with a speed test to check that they got what they paid for. Now we're in the era of more diminishing returns in terms of, you know, increasing speed beyond a gig now. But if we move into this third era of trying to improve responsiveness and reduce latency, what are the coupling mechanisms between the network, the application outcome, and the customer experience? So this is a challenge. But fortunately, there's a lot of good work going on in this area in different standards bodies. So first of all, if we just look at the yellow areas here, so we've got, you know, as an example of network performance, quality attenuation standardized in the BBF, including how you use STAMP and TWAMP to measure that. Yesterday, Francois from Meta showed a whole area of where you know, the ITU has done work on application quality of experience metrics for different types of applications. And then customer insight studies, a lot of application developers and network operators have done their own studies and surveys there, focus groups. And this is an area where cable labs in particular are extremely strong in doing primary research on these kind of things. But really what we need is a common language for application developers and network operators to speak to each other. And this is where things like quantitative timeliness agreements come in. The BBF has done some work on that, and this enables a network operator to share capabilities and an application developer to share requirements in a common way. And the quality of outcome approach in the IETF that Magnus will cover tomorrow, that kind of builds on some of the principles there. And then we've got the work going on in Cable Labs and Kamara around APIs to share, you know, quality on demand and quality of outcome capabilities. And then, as we heard yesterday from Francois, there's the new work in TIP around trying to link the network performance and quas, etc., to the customer's experience, and that's extremely interesting. So I think that, you know, if we can understand and quantify and standardize this area and really understand this coupling mechanisms, that will really help us. And in some of that tip work, they've talked about the need for application aware networks and network aware applications. And so I think these purple lines here are important to develop that thinking and really understand this coupling. And then the final area I wanted to talk about was the issue of, you know, proving that there's a benefit here. So if a customer orders a broadband product with low latency, how can they prove for themselves that they are getting what they ordered, and maybe they had to pay for that as well? So in the first era of broadband, where it was about speed, that was kind of easy. You know, they had a speed test app. They paid for an uplift in their speed tier. They could test it, and great, I got what I paid for. I'm happy. But a lot of the latency improvements we're talking about involve specific packet marking, you know, per application class, device, or whatever. And yes, you can provide, ways of proving that to a customer. We could do that in our own My Vodafone app or Vodafone broadband app. We could do things. A lot of the application layer, the apps themselves will have their own metrics, but sometimes a customer may not necessarily trust the folks who provided the application or the network, and they want an independent test. And the trouble today is the latency test baked into those speed test apps doesn't mark packets. So any improvement you're making in the network will be invisible to those kind of latency tests there. So that's an issue. How do we have that conversation with the customer, and how do they have that independent ability to test that they get an improvement? So in summary, I think we're entering a third era of broadband beyond just speed and capacity, and responsiveness is becoming increasingly important. We do have lots of technologies to improve latency, but that technology push by us in the engineering community will only get us so far. And I think if we want to improve the customer market pull of reducing latency, I think we need to address the challenges around demarcation, quantifying the benefit, and proving that benefit. And as I said, there's a lot of good work going on in various standards bodies in these areas. So if this is an area you're interested in, I would encourage you to get involved, because there's more challenges and more problems to solve, and we need to throw good people at it to move the state of the art forward. Okay, thank you.
Thank you very much, Gavin. Very interesting. We have to jump to the next speaker. So please do the Q&A. Type answers for the Q&A.
Okay.
Thank you very much. All right. So our next speaker is Koen de Schepper. He is the research principal at Nokia Bell Labs, and we'll be talking about L4S in some more depth, I believe. All right. We can see your slides, Koen. Will you turn your camera on as well, or no? And you're muted at the moment, so I can't hear you.
Yeah, you should be able to hear me.
Excellent. Yes, now I can hear you and I can see you.
And we
Thank
can
you
see.
very much.
Okay, great.
Take it away.
Okay, thanks for the invitation also again. Last time I've discussed what are, let's say, what makes it easy and how L4S makes it easier to deploy a low latency service, and to make it also more robust, and so that and let's say less manageable or less to be managed, where all these worries or extra cares can be left unmanaged, let's say, and kind of resolve themselves by the interworking between the network and the applications. And at the end, it's much easier to focus on the real latency, and whatever we improve on, let's say, that base latency, which is important as well, that this can be optimally benefited and focused on. And that we in the internet finally can also benefit from those improvements in the technology by removing all, let's say, or potentially all queuing latency. But this talk, I want to dive in a little bit more into the Prague congestion control, and especially we said in the past always, okay, we need to build a queue for classic congestion controls. Why can we avoid this for Prague, and how do we avoid it especially? So to dive in immediately in the topic around latency, the obvious thing when we want to reduce latency is, of course, to have an active queue management system. Instead of having the tail drop, we can kind of have a controlled loss, where if the queue grows too much, we start losing a few or explicitly dropping a few packets more. If the queue starts to drain too much, we can reduce these extra losses. So we can control at the end to a certain delay target the queuing latency of a classic flow. But it's only limited, let's say. We still have to cover these variations in the sawtoothing. And also at the end, delay-based congestion controls needs to see a latency. So a queue needs to be built up. Latency has to be created if you want to control delay-based congestion controls, especially if you want them to have a measurable out of the noise that always is there in the internet and an actionable delay. But there is a limit also on what active queue management can do, and the problem is the lower you make the target, the higher you have to start dropping packets, and having really low latencies is for high rates it's possible. For really low round trip times and maybe lower throughputs, the loss rate is a big problem. So we have to limit the loss rate by still allowing a big queue. ECN, of course, is a solution there. And in the past, RFC 3168 did propose to, instead of loose packets, mark them. And the active queue management system, of course, allowed to keep packets which are marked. But the problem was, okay, we have infrequent markings, which are still the same as drop. And for loss-based congestion controls, which are still in the same queue, we need to preserve also the same big queue, and all the other reasons why we had the queue up to now are still valid, even if you partly support ECN. So the bigger change was the introduction of data center TCP with ECN, a better use of ECN, where we have a very frequent marking. We kind of excluded the support for drop-based congestion control. Although data center TCP responds to drop if drop happens, it's not assuming that it has to be compatible with other drop based congestion controls. It has a smooth throughput. So a lot of these reasons why we need to create a queue were removed, but still looking into more the details, let's say, and trying to use data center TCP on the internet, we see that data center TCP in a data center is still having a queue around the base round trip time, which is of course very small in a data center. But in the internet, this can vary a lot, from milliseconds to or hundreds of microseconds, maybe to hundreds of milliseconds. So let's have a look what is then additionally added on top of RAG compared to data center TCP. These are important things that had to be done to make it work better on the internet. First of all, if you can have the threshold bigger than let's say the base round trip time, or in the same order, you can have large bursts within a window of data. You can have ACK pacing. All these things work pretty well. They don't have a big impact because they stay below that round trip time level of delay that they create in a queue. But if you have, let's say, a big round trip time on the internet, a large burst will cause a lot of marks, and that's why if we have these thresholds way below this round trip time, these large bursts for TCP segmentation offloads, which actually makes data centers work more performance by having packets. The TCP stack can make packets of 64 kilobyte on a 100 gigabit link. They only take 5 microseconds, but on a 100 megabit link, they take 5 milliseconds of latency. So we had, and of course on a 10 megabit link, it's 50 milliseconds, which is of course not possible if such a big packet is segmented in a network interface and then back-to-back sent over the internet. So we had to reduce these burst size, limited to what, and we took a number around 1 millisecond. So if the burst is would be created in the current rate that we know that we have to use. If that would be bigger than 250 microseconds, we limit how many packets we create, or the size of those packets, which is okay because these rates are much lower, and this is made to support hundreds of gigabits. Here the rates are much lower. So there is not that much need for doing this, but also pacing the packets. So if we have those smaller bursts, they need to be paced, and mainly to make sure that all those small bursts of 250 microseconds potentially, they kind of join in with each other. They can arrive by accident or sometimes meet each other in a queue, but that only then takes, let's say, 500 microseconds if 4 by accident join, and so on. But that's then really if there is the limit in here. Another reason why this pacing is so important is that you have to be nice to your neighbors. The goal is that you arrive at the bottleneck and you kind of evenly mix in with each other without creating big blockings here. So it's important to be nice to your other RAG L4S flows, but also it's important to leave enough space between all those packets or those bursts, those micro bursts of packets, to make sure that classic traffic can fill in those gaps. And if you probably have recognized a dual pi square or dual Q coupled AQM mechanism, which is also an RFC standard. In here, how it works is that the scheduler here needs to make sure that this queue is emptied. So it needs to have a low latency scheduler on this queue. And then, of course, it needs to have a queue building queue, because we need queuing latency before we want to drop, or even before we want to activate our AQM with losses. But we need to build a queue, so we have to block this. But of course, we have to make sure that it can fill in all the gaps that are left by the Prague congestion control. And then if the queuing latency becomes too big, the active queue management here gets active, and it will start dropping these packets, but also then marking these. And actually the marking, this coupling marking, make sure that the L4S leaves more space if it's necessary, or less if the congestion goes down. Or I shouldn't say congestion anymore, but the rate management or whatever, the latency management. So to make more space so that the throughput of those flows can be balanced correctly. Another reason not so often known is why you need a queue in a classic network is because the congestion controls classic are round trip time dependent. That means that if you have 1 millisecond base round trip time, the idle latency, you can send like 1,000 round trip times per second. If you have 100 milliseconds round trip time, you can only send 10 round trip times per second. So this guy, the problem is that they converge, let's say, the rate to the same amount of packets per round trip time. So this can get 100 times bigger throughput. So if you add 100 with 1 millisecond latency, if you configure your active queue management to 1 millisecond, besides the high loss rate, if that's still feasible, you also have a big small extra round trip time. So for this one, it sees in total 2 milliseconds, for this 101, and the rate ratio will be very high. That's exactly the same for data center TCP. So if you want to keep these queues very small on the internet, where we have this big range of throughputs, we also will get a very big range of throughputs, from round trip times, we will also get a very big range of throughputs. How is it solved in the classic world? Well, typically, if you have an AQM with a bigger target, then you quickly reduce this rate ratio. If you put 100 milliseconds as an active queue management system, a bigger target, you get only a rate ratio of 2. If you put 1 second, they're almost getting the same throughput. So the bigger the queue, the more fairness. Of course, that's not what we want for Alpha S. We don't want a big queue. So we had to find another solution. And that solution is to, even if there is, let's say, no queue at all, you purely mark for rate control. When, for instance, there is coupling between those two queues, the latency is 0. So 1 to 100 would be 100 rate ratio. Well, we make Prague response if they are lower than 25 milliseconds round trip time, respond them to as if they are 25 milliseconds. Maybe also less known is that there is also some kind of, and this is maybe another responsiveness, but responsiveness to how fast you can fill available bandwidth. You could call it also the inertia of a flow, like the bigger the round trip time, you could say the more heavyweight the flow is, because it has more mass and responds slower to marks. And if you have a very lightweighted or low round trip time flow, it's actually very responsive. And when there is a reduction in throughput over time, it's the one who is, you could say, getting bullied by the heavyweight. He's going to adapt the whole time and is going to have some kind of sausage throughput, which might be wanted or might not be wanted at all by the applications. So if these throughput variations are smaller than the round trip time, it's impossible for this congestion control to even adapt. So you will always have this to a certain extent. Today, the Prague congestion control kind of also balances this inertia, this responsiveness. And if you have a flow of 25 milliseconds and one which is 1 millisecond, it's not only going to get the rate of the 25 milliseconds, but also going to get this inertia, this responsiveness. So this is, you could say, a missed opportunity for throughput, but on the other hand, the application gets a very smooth throughput for streaming. This is perfect, of course. For downloading a file, it's a missed opportunity, but like said, there is plenty of bandwidth. We want low latency, so we also shouldn't take risks to quickly grab bandwidth and then get into the problems if there are frequent reductions in bandwidth as well. So that's also an aspect from L4S, which is maybe less known, but it's also a matter of a compromise. Here you see an example of a few blue L4S flows and orange classic flows. And one of these flows is, for instance, video, which sends data in chunks and has a certain on-off behavior. Well, you can see having a buffer in the network has a big advantage, because you can immediately fill in those gaps. If other flows stop, you see this big buffer of this one flow, this classic flow, can immediately take a lot of bandwidth because it has there available in the network. And you see Prague will only, the blue ones, L4S, will only after a few seconds maybe join in and get the same bandwidth. You also see they get a smoother bandwidth, less noise. The classic can fill in if it's a noisy channel, completely fill in the bandwidth at any time because they have buffer enough, and it doesn't need to be a big buffer. A few hundreds of milliseconds might be good enough. And you see Alpha-S gets perfect low latency, but cannot use immediately, let's say, scheduling opportunity. So there's a compromise. And that I think is good also to have these two types of traffic that applications can choose. I'll come back to that later. A more recent improvement also that we did in Prague is to do pacing below the minimum window. The minimum window means that we need to have always at least 2 packets in flight. And that means if your round trip time is, let's say, 10 milliseconds, okay, we can control down to 2 packets per 10 milliseconds. It's 2.4 megabit. It's not that low, but it's low enough for today's networks, most fixed networks at least. But if we start having more flows, this number becomes already bigger. And if we have really low latencies, round trip times, one flow can already not be controlled below 240 megabit. Imagine 100 flows, you need at least 24 gigabit. So that means that we will need to build a queue, that we don't have spacing in between those bursts when we reach that rate, and they become uncontrollable. So that's why we reduced the code, or we changed the code of Prague currently in a rate-based testing branch, where we use fractional windows, so to reduce the pacing rate in smaller steps as well. And if that window is so it can also then go below a window of 2. It can be very small. And we can reduce the pacing rate lower, and then the pacing rate will become the bottleneck. And the real window can still be kept to 2, but it's not blocked by the window. It's then blocked by the pacing rate. But we also saw for very low round trip times, and typically when the window is below 4, that the smoothed round trip time can become very unreliable. And that's why we start updating the pacing rate in this new code. And we calculate the window from a more stable, highly smoothed round trip time to get a stable pacing rate. We also made sure that you can always send 2 packets every 25 milliseconds. So we need 2 marks per 25 milliseconds. Only at 50%, we get only 1 mark per 25 milliseconds, but when the marking probability becomes higher, the rate becomes lower. So with this new code, we still can have in the both extremes 2 mark packets per 25 milliseconds. We can go down to 100 kilobit, and we can always, even at 100 kilobit, send a packet every 12 milliseconds. So you could still do, let's say, 80 frames per second video on smaller packets. Okay, so I think it's good. Okay, all the applications that need low latency can use LFRS, but there's still also a big benefit of having a queue in the network, especially for mobile, very fluctuating networks, where also low latency can be very expensive, or use more resources than something which can have a backup in the network and completely can fill in all the gaps in the network. So I think it's good that the network doesn't have to choose between those two worlds, where we have no queue or we have a queue. That it's better that the application can make the choice. And when you don't mind whether your task is finished in 1 second, you better can use still the classic. If you think it should be below 1 second and the rate is not that important for you, you can definitely use LFRS if you want interactive interaction with your applications. Okay, this is a quick recap. I think the main message is Classic can fill in gaps in the network because it has a bigger queue. Let's take the advantages, and it needs a bigger queue for other reasons, but that's okay. LFRS can run without a queue in the network, but of course can't fill in all the gaps, and it also has its limitations. But definitely, we get the low latency that we need for more and more applications. Okay, that's it.
Thank you very much, Cohen. There are a few questions, so let's do a couple of those.
So I read the first question: is there a final value in low latency?
Sorry, that question was for Gavin. I think that's already been answered somewhere else.
Where does it start? Is the next one?
Yes.
Is it possible to hit 250 microseconds on a Wi-Fi link? I don't understand fully that question. How is it possible to hit?
I suppose the question is how can you have that short of a queue on a Wi-Fi link?
Yeah, well, if you only send 250 microseconds of data, the Wi-Fi link will take it, will hopefully be able to send it before the next 250 microseconds comes in. Wi-Fi might be blocked depending on how it's, let's say, configured and what is the other traffic of others. So it might aggregate those 250 microsecond bursts and send them out in a bigger burst. That's known, and there it's also, let's say, important that okay, Prague can now reduce the latency, but of course the networks have now the responsibility to make use of this capability and make sure that they can also keep bursts within those 250 microseconds. So it's an opportunity, and it's, of course, if the network is very bursty, we can't solve that with Alvarez. But now it's an opportunity to also better improve it.
All right, thank you very much. I think so. We are intending to have a break before the next speaker, so I think we will move to that now. So
okay.
We will take a break for the next 5 minutes, and we'll be back at 1740 Central European time. So it's a 5-minute break. And again, thank you very much, Cohen. There are more questions, so if you do have time to answer those in writing, that would be cool.
Okay.
Thank you very much.
Bye.
All right, so we will get started in about a minute. Hey, Neil, we can see you.
Hi there. How's the audio?
It's very good.
Okay, great. Sorry.
Yes. All right. So our next speaker is Neil Cardwell. He's a principal software engineer at Google and has been working on the BBR rate adaptation algorithm. Is a new term I heard. So, Neil, please feel free to share your slides and get started.
Great. Here we go. Let's see.
Yep, that is working.
All right. Are we full screen?
Yes.
All right, great. All right, thank you very much for inviting me here today to speak. I'm going to talk a little bit about, well, I'm going to apologize first of all, because I agree with Stuart Cheshire's point that we ought to try to move toward phrases involving rate adaptation and things like that. But I apologize, these slides are inherited from previous talks, and so don't use the preferred nomenclature. But I'm going to talk about BBR congestion control and its approach to tackling latency. And this is joint work done with my colleagues at Google. And I want to thank them for all their work as part of the team. And so let me start with a background here about the problems that motivated BBR congestion control. So the story goes back to about 2013 or thereabouts. And we were seeing in our team, the congestion control group at Google, that many Google services were complaining about various TCP performance issues. And we were seeing a lot of different problems. So on our internal high-speed backbone network called B4, we were seeing sometimes TCP throughput was often less than 10 megabits per TCP connection, even though this is a multi-gigabit network. We were also seeing on YouTube that sometimes there was bad video quality with round trip times, sometimes above 10 seconds, if you can believe that. And then on google.com, we were seeing poor latency in developing regions. And as a result, a lot of different services started to use various tricks and workarounds to improve TCP performance, such as using parallel connections, tweaking TCP performance tuning knobs, and adding more buffer to the network. So what's going on here? So the root cause of all of these problems was basically that at the time, the TCP congestion control at Google was using the Linux default, which was an algorithm called Cubic. And Cubic is what we call a loss-based congestion control algorithm, where packet loss was the sole signal that it's using to decide to figure out how fast to go. And the issue with loss-based congestion control is due to its basic behavior, which is that a loss-based congestion control will continue to accelerate, sending at higher and higher rates until it sees a packet loss. And this is a problem because this is actually a very widely deployed approach. There are two main algorithms that are widely deployed that use this approach. One is Reno, which is the official standard for internet congestion control, and it dates back to the late 1980s, and it's still used today widely because it's used by Netflix. Cubic is the other big one, and it's widely deployed as the default congestion control now for all of the major operating systems. And the issue it really is that packet loss alone is not a great proxy or signal indicating congestion. And you can think of the issue here as having a spectrum of issues. And at one end of the spectrum, if we imagine a network bottleneck that has shallow buffers, you're going to see that flows are frequently suffering random packet loss, and that's going to cause low throughput for loss-based congestion control algorithms. And the basic issue is that here in this kind of environment, packet loss is coming before sustained full utilization. And in those environments, loss-based congestion control reacts to those losses and gets low throughput. And if we consider a sort of benchmark flow that is trying to achieve 10 gigabit throughput over 100 millisecond round trip time, you actually need a tiny, tiny packet loss rate that kind of needs almost scientific notation to describe in order to achieve that throughput if you're using loss-based congestion control like cubic in this case. And if we consider a more achievable loss rate, like a 1% loss rate that's fairly common over the public internet, then over 100 millisecond round trip time, that's going to give you a throughput with Reno or Cubic that's actually less than 3 megabits per second. And at the other end of the spectrum, if we think about a path with deep buffers, what's going to happen with loss-based congestion control is that the flows are going to suffer low loss, but they're going to have very high delay because the flows are going to keep increasing their sending rate until they suffer packet loss. But by that time, that large buffer will have accumulated a large amount of data. And that particular problem is a problem that has been dubbed buffer bloat. And so you've probably heard about that if you're attending this webinar. So what is causing that? Well, you can sort of understand the problem a little better and think about ways to solve it with even really a very simple model of a network path. And so here's a very simple model that consists of a network sender on the left, and then a data receiver on the right, and then a network path in the middle. And you can see the data packets traveling along the top from left to right. And then at some point in the network, there's the slowest link, which we call the bottleneck link. And if the sender is sending faster than that bottleneck rate, then a queue of data packets will start to build up there at the bottleneck. And then those data packets will make it through that bottleneck link, arrive at the receiver. The receiver will send some sort of acknowledgement back to the sender, and the sender will use those acknowledgements and any signals that it can infer from those acknowledgements to decide how fast to send over the network. So then with that model in mind, we can start to analyze what happens as a network flow, say a TCP flow or a quick flow, starts to send faster and faster over the network. And here we've actually got two different diagrams on top of each other because they share the same x-axis, which is the amount of data in flight that a particular transport connection, TCP or quick, has in the network. And then we can, in the bottom graph, we can think about the delivery rate that the flow is achieving. And then in the top graph, we can think about the round trip time that is resulting from the behavior. And so if we start over here on the left, and I hope you can see the cursor, if we start over here on the left with a small amount of data in flight, say the initial congestion window of say 10 packets is common, as the flow ramps up, typically in a mode that we call slow start or something similar, it will send exponentially faster over time and will achieve higher and higher delivery rates until it reaches some point where it's fully utilizing the bandwidth supported by the bottleneck link. And at that point, of course, if it puts more data in flight, it's not going to go any faster, but those packets, those extra packets in the network are going to sit in that queue that we saw at the bottleneck link. And as you put more and more packets in flight in the network, that queue at the bottleneck gets longer and longer. And what that does is that increases the delay that those packets are going to experience as they're waiting in that queue. And so a loss-based congestion control algorithm is going to put more and more data in flight until it's completely filled that queue and then starts to experience packet loss over here as it's filled up the entire size of the buffer. And at that point, the loss-based congestion control is experiencing maximal delay and then some amount of packet loss. And as a result, you end up with high delay over that path. And at the other end of the spectrum, if we imagine what happens with loss-based congestion control in shallow buffers, then what happens is that as these flows ramp up, they're only able to increase the amount of data in flight a little bit before they start to experience loss. And then these algorithms are constructed to cut their sending rate by a fixed fraction, by either 50% of its Reno, 30% of its cubic. And so they've made a very large multiplicative decrease, even though there's only a very small amount of extra data in the network. And so what they end up doing is, over time, they end up underutilizing the available bandwidth. So they have a very low throughput and very poor utilization. So as you've been thinking about these scenarios, we can ask, what is the optimal operating point? And you've probably already intuited that that spot is right there, where you've achieved the maximum bandwidth and minimum round trip time. And that point has a special name that's already been on the diagram here, which is in the network, that's the bandwidth delay product. And so you can get that by multiplying the bandwidth of the bottleneck link times the minimum round trip time of a flow. And then we can sort of ask, well, is there a way that we might systematically try to approximate that operating point with some kind of congestion control or rate adaptation algorithm? And one approach would be to say, well, let's try to estimate that minimum round trip time with some sort of simple windowed filter where we take the minimum of the round trip time samples that we've seen recently. And in this case, we can imagine that those samples over the last window are these gray points. And then we see the minimum here is pretty close to the minimum round trip time. And then analogously, we can say, well, what sort of approach could we use to try to estimate the maximum bandwidth available to the flow? And one simple approach would be to say, well, let's try to take the windowed maximum of the recent bandwidth samples. And again, here are some samples, and you see the maximum here in this case is pretty close to the maximum bandwidth in the diagram. So that is basically the basic intuition behind the BBR congestion control. But before we move on, one interesting thing that's important to point out is that particular flow actually at any given time, it has to make a decision about, in any case, it will end up being on either the left or the side of the BDP or the right side of the BDP. And if it's on the left side, only the minimum round trip time is visible because it only has a smaller amount of data in flight, and it can measure the sort of unloaded round trip time of the path, but it can't achieve the full throughput. And by contrast, if the flow is over here on the right side of the BDP, it can measure the maximum delivery rate, but then it can no longer actually view the minimum round trip time because there's always some amount of queuing. And so to be able to measure both of those parameters, the minimum round trip time and the maximum bandwidth, that actually has to spend some amount of time on the left at that point and some on the right at that point. And that, in a nutshell, is BBR congestion control. So BBR stands for bottleneck bandwidth and round trip time. And the basic idea is sort of to dynamically model the network path, tracking, as we were discussing, the windowed maximum bandwidth and minimum round trip time that have been recently observed by taking measurements from every acknowledgement. And then once you've got that model, then you control the sending rate based on that model. And you pace near the estimated maximum bandwidth, and then you bound the amount of in-flight data in the network from that flow as a function of the estimated BDP, and you keep it close to the BDP to limit the queuing and queuing delay that the traffic experiences. And then you sequentially probe by spending some amount of time, trying to spend some amount of time on the left of the BDP and some on the right of the BDP, so that you can probe the bandwidth and the round trip time of the path and feed the model samples and keep it fresh and more accurate. And then the basic approach is to try to seek high throughput with a small bounded queue. And as a result, the algorithm in practice typically can approach the maximum available throughput for some targeted level of loss. And then it can maintain a small bounded queue that's independent of the buffer depth. So what does that look like if we try to visualize what the pieces are of this algorithm? You can think about it as sort of the algorithm here being this gray box, and into it you feed some input signals, such as throughput and round trip time, and also loss and ECN in later versions of the algorithm. And those all get fed into the model, and then you have the algorithm use that model to estimate these key parameters of the bandwidth and minimum round trip time of the path. And then there's a probing state machine that makes decisions about speeding up and slowing down, and spits out 3 control parameters: a pacing rate, a congestion window, which bounds the amount of in-flight data in the network, and then some quantum of how big a packet burst you want to send into the network. And then those go into a pacing engine that takes some stream of data from an application, say writing into a socket, and then it chops that data into bursts of the quantum size and then paces those out into the network. So what does that give you? So there are 2 scenarios, again, 2 ends of the spectrum, where we can analyze, what are the properties of the algorithm. So if we consider what is the behavior of the algorithm, it's scaling behavior as we increase the depth of the bottleneck buffer. We can see here on the x-axis, as we increase the buffer size, we can look at the round trip time latency. And as we've been discussing, Cubic, because it's always going to fill that buffer and then keep it near full, as you increase the size of your bottleneck buffer, the latency for the traffic going through that path gets higher in a very linear fashion. Whereas BBR, because it's basing the amount of in-flight data on its estimate of the path's BDP, it bounds that latency to a fixed amount that's independent of the bottleneck buffer depth. So at the other end of the spectrum, if we consider what happens in shallow buffers where you get random packet loss, you can think about what happens as you vary the random loss rate in the x-axis and ask what is the good put or throughput you get on the y-axis. And as we were discussing, Cubic as you increase the packet loss rate, both Cubic and Reno will decrease their throughput very rapidly, so that at typical loss rates we see on the public internet of around 1%, you get very low throughput potential. Whereas BBR is designed to tolerate random loss up to some target level and achieve a high throughput that's very close to the maximum throughput up to that level. So, that I will. So as BBR has evolved over the years, we've improved it, and we've made the model richer to explicitly model aggregation effects that we see in the network and the maximum amount of data that we can put in flight before we see ECN or loss. We have enriched it so that it can use ECN signals, that is explicit congestion notification, like DCTCP or L4S ecosystems. We're continuing to improve the algorithm. I think we're running short on time, so I won't go into a detailed evolution. But suffice it to say that we've made various releases over the years, and you can find the most recent release on GitHub at this URL down below. And BBR has been used both at Google and a number of other places. And there have been some interesting papers analyzing its deployment and how frequently it's deployed. So just a quick summary then of the various algorithms that have been widely deployed so far for the public internet for TCP and quick congestion control. There's Reno, which is still the official IETF standard, surprisingly, but it suffers high latency in deep buffers, and you can sort of see that that's because its congestion window on the y-axis that's limiting the amount of data in flight always goes up to the point of packet loss and then cuts in half and then linearly ramps up until loss again. And because it's only linearly ramping up, It's got a non-scalable linear growth. That means for very high rate paths, it takes a long time to return to full throughput. And as a consequence, also, it has low loss tolerance. And to fill a 10 gigabit, 100 millisecond path, you need a tiny, tiny, minuscule, infeasible loss rate. Cubic is a loss-based congestion control built to improve upon Reno, and it does, although it still suffers from high latency, and its growth curve, although more scalable than Reno, still is not as scalable as one would like, and it still has fairly low loss tolerance. For 10 gigabits over 100 milliseconds, you need about 40 seconds between losses. BBR, by contrast, is built to try to achieve low latency in deep buffers and have scalable exponential growth when bandwidth is available and it can ramp up safely. And it's designed to be tolerant of loss up to some design parameter to be able to achieve full throughput in shallow buffers. So in conclusion, I've talked a bit about BBR, which is a model-based congestion control that our team developed. And it's evolved over time to have a richer and richer model using diverse signals such as delay, bandwidth, and now loss and ECN as well, of course. It's been deployed at a fair number of places at this point. The code is open source, so we encourage you to check it out and gain experience with it, and give us feedback or provide patches if you have ideas. And it's a work in progress. We're always working on improving BBR and moving beyond it. Our team is working on algorithms that support L4S ECN, which you've heard about today, as well as generally reducing latency and loss and improving coexistence with classic Reno and cubic algorithms. And of course, this is an open source project, and we welcome feedback and contributions and ideas from the research and user community. So thank you very much. And I guess we'll take questions if there's any time.
Thank you very much, Neil. We are a bit short on time, so I think we'll do the Q&A in writing, if you don't mind.
Sounds good.
Thank you very much. So we'll jump straight to our next speakers. Thomas Zinner and Katrine de Moor, both from the Norwegian Technology of the Norwegian University of Technology and Science. And please, Thomas and Katrine, take it away. We can see your videos.
Sure.
And I can hear you, Thomas, and I can see your slides.
Super. Thanks a lot, Björn. Thanks for having us here today. It's a pleasure to provide our view on latency. So I will give the presentation today with my colleague Katrine de Moor. Thanks already for the short introduction. I think we also keep it short because of time reasons. And our main theme, which we also discussed a bit while preparing the slides and for this talk, is: do we understand the impact of latency on apps and users? And when we just think about what today's internet consists of, we already had a couple of different applications which were named today, but there's a lot of. There are old legacy applications, the normal communication, telephony, video conferencing, messaging, but there are always coming new applications into the game. Yeah, it started with web browsing, video on demand, and live video streaming. There are also talks about live video streaming with Dash, for instance, in the seminar. We have the online social networks, the rise of the social networks a couple of years ago. Now the next big things to come maybe are VR, AR, XR, haptic applications, and the Internet of Senses. And as always, the Internet is always surprising us, what will be then the next one. But if you just break it down, we have this large application diversity. And we have the underlying transport protocols, which somehow take care about sharing the available resources, and the resources are, as we also saw on the previous talk, some are about the throughput, the bandwidth, but also about the corresponding latency. And also the problems we are having because of all the different buffers in the networks, the different way the transport protocols are designed, to which extent they use loss as indication for packet loss or delays and things like that. So if we just take a look about different applications like a bulk data download and a YouTube application or a Netflix application or something else, a video streaming, then we typically end up in something like the fair share with respect to the quality of service. So somehow equally share the bandwidth in a fair manner. That means the data download performance is good, but of course, it's what we all expect. It's what we all know also, or have also been exposed to in the past. We run into this buffering. So the video buffer is not able to completely fill up. It drops to 0 and the video stops. So stalling is happening, something which has been predominant in the past, got better now with adaptive video streaming, but still something we were experiencing a lot of. So our YouTube quality is bad. The question also is a bit now, why is it bad? What are the reasons for that? Because what we would like to have in the end is a constant high buffer playtime, and based on that, then of course, a continuous video playback without any interruptions. And to achieve this now, we have two things which can help us with that. The first is network-aware application design. So how do the applications try to cope with these issues and to improve the situation, adaptive video streaming being one of the techniques to mitigate this, and application-aware networking. So all these different possibilities in the networks to be able to provide better bandwidth, higher bandwidth for the end users, to make sure that no bottlenecks or less bottlenecks exist, and also how to cope with fair sharing of resources at bottlenecks. So when we take a look about this now, this is now also something where it goes beyond the technical system, beyond the technical domain, but also somehow reaches towards the user. And this is also the quality of experience. The term was already named by Björn in the beginning. It's also one of the important research areas which tries to address all these issues. So we have the quality of experience, QE, and we have the quality of service, QS, on the other side. QoS focusing clearly on the technical performance parameters, while QE focuses on subjective user perception. So in the end, about what of the different QoS parameters is now really important for a given application. And here it's now also very important to understand the relationships between the quality of experience and the QoS. So that means also what are key QE influence factors. So what is now really important? Is it bandwidth? Is it throughput? Is it the burst throughput? Is it the delay, the latency? Is it the average RTT? Is it about outliers? And also about how to measure them. And on the other side, you also need to be able to understand what the impact on the user. There it's also getting a bit more tricky. We are going towards the user. We want to have to ask him, we have to interact with him. We have different assessment methodologies where we can do that. We can do it in lab studies, which are very controlled. We can do it in field studies, somewhere outside, while asking the users while they're using the bus and surfing on the mobile, things like that. Or we can do crowdsourcing tests. And this all helps us now to develop objective QE models. And they are important for the identification of root causes of unsatisfactory or degraded quality of experience. So I now would like to hand over to my colleague Katrin for going a bit more into the direction of quality of experience, and particularly also about those assessment methodologies and about problems with them.
Okay, thanks, Thomas. Yeah, I think you will need to move the slides. So yeah, so if we want to try to understand how latency influences QE and thus the user, we need to also look at this from a kind of more holistic perspective. We need to think of the experience and quality of experience. So this model here is aiming to show a little bit the complexity there. I don't have a technical background, and for me, the technical system is very complex. But in this figure, you also see that if you want to look at the user side, there is also a lot of complexity. So what this visualizes is basically a person turning into a user in interaction with a product. I probably don't see my pointer now. And this happens in a certain context. And of course, this context is not necessarily something that we can control as user or as service provider, but it will influence our experience. And you also see these circles here in this figure, which represent a use process, because something might change in terms of sensitivity to different types of impairments or different types of situations. becoming used to using a system and so on, something might change there along the way in terms of how critical certain impairments are. So if you move to the next slide, Thomas. Yeah. So what has happened within the field of QE over the last years is that, you know, we kind of joined forces a little bit within this community and try to move forward towards having some sort of taxonomies of, okay, what are now these main influence factors? And influence factors here are then characteristics of either a user, system, service, or the application or the context in general, which may have an influence on the QE for the user. And we basically group them into three big categories. The system ones, which I guess most of the people who are in this session are most familiar with. And then context-related factors such as the physical context, the social context, the temporal context, and so on. But also human aspects. So whether it's stable or more dispositional or more changing human states, which may influence our experience either directly or indirectly. So Thomas talked about QS, QE in the beginning. It's a kind of a simplified view here, but QS has been covering mostly the system level, as you see, while QE is much broader. And the point here is that if we really want to understand the impact of some of these technical parameters and dimensions on the experience of the user, we can't just ignore the other ones. Move on. Yes. So what is actually the problem with this? So it's very good. We moved on within the community. We have a better overview. We have a body of research that is providing more and more empirical evidence for some of these categories of influence factors, which is good. But still we have an issue that we have this more theoretical understanding of what might play a role here. But it's very difficult once we move towards either the human aspects or also towards the context, operationalizing some of these dimensions and factors becomes really challenging. So that's one challenge that we have. Another challenge is that the tradition has been to look at these aspects more in isolation. So we also lack kind of best practices to really study some of these factors in combination as well. So we need actually more development of new approaches, and that's kind of the main message of me today in this perspective. So we have lots of recommendations by ITU on how to conduct subjective studies. Subjective studies in this context are basically studies that involve users to understand specific impact of chosen, in most cases, technical parameters and variables on QE. So there are lots of recommendations out there, but there is a but, because these recommendations, and especially the older ones, they make a lot of assumptions. They are based on a very experimental design paradigm, meaning that, you know, we want to have very high internal validity. We want to be able to know or to be able to say that, you know, this variable has a direct influence on the QE, on a kind of outcome variable. And we kind of make sure that we study this in a kind of gray box. We study this in a context which has, as I said, a lot of assumptions. Viewing distance is measured. Everything is kind of controlled, except for the factor or factors that we want to investigate. So basically, we obtain results. They are comparable across labs. Very good. But again, there is a but. Can we actually extrapolate these findings so easily to the realistic context or to the real context of use? So this golden standards that is used for what Thomas mentioned, the objective models, it can be challenged. So one observation that has been raised within the community over the last years is this need for more innovative or different approaches. We move on. Yeah. So one of these dimensions that, if I refer back to the first model I showed you, these circles, is the temporal dimension. So what happens when let's say we want to do an experiment, we want to study latency in the context of telesurgery application. and we bring people into a lab setting to test this, and we have different kind of latency scenarios and so on. We want to investigate precision, we want to investigate the task completion time and so on. And we do this only at one point in time. It's obvious that there will be a set of human characteristics that will come into play, but also this temporal dimension. Might be that once one gets to do the same procedure several times and so on, something might change. So the problem is that many of the studies take a cross-sectional approach. So basically we bring users into a lab, we test, we have a set of measures that we take, and then this is part of the golden truth that we establish. But we don't consider that in the real life, we interact with services for a longer time. Our habits change, our experience changes, our expectations also change. So this is one of the dimensions that we have been working on, where we need novel approaches. Thomas, the next slide. Another set of examples here is what I called here, how, who, and where. So I think the one more or less in the middle on top would be an example of a kind of more or less classical video experiment with a big screen here, but you see already that it's a controlled environment, it's artificial lighting in a certain setting and so on, versus the other side that, in many cases when we watch stream videos or we watch Netflix or whatever, we are in a social setting potentially. So, and we have very few studies that take this into account or that have tried to also model this. The other example there on the bottom left corner, task context. So one of the things that we have, for example, seen in some of our studies is that when we do a classical video experiment with YouTube content, for example, people are able to rate the quality. We can look at different types of impairments. But when we then ask people how the experience was they would answer that it was strange because I wasn't able to use my phone, which I would otherwise do. So this dimension of how we use different services in parallel all the time is something that we need to take into account in our study designs, because it basically changes our perception and our attention. And also the device. So you can move to the next one, Thomas. Yes. And here one last example where I would make some advertisement for our good colleagues at the University of Zagreb, which this is a thesis that actually will be defended in January, early next year, on VR gaming QE, and amongst others also looking at, they did several studies on latency, for example, in the context of multiplayer VR games. And what was interesting there, I don't have numbers here, I'll just give you what I think is a really important takeaway, is that even though several of these studies were really designed to investigate the impact and to kind of really pinpoint the impact of latency, different latency scenarios on the QE experience, but one of their conclusions was that even if an experiment is designed in such a way that this broader context, the social interaction around between the two players, how involved the two players are, the specifics of the game itself, we see two illustrations here, really need to be considered also in the evaluation. So it's not enough to just focus on this particular, look at the latency scenarios and ignore these other factors, because they play actually a really important role. So for example, in this case also, one is Blasten, it's a first-person dual first-person shooter game, whereas the other one is this ping pong game. So both games have very similar characteristics, but through their study they were able to show that the network degradations had a much more noticeable effect on the tennis game, so that there were better lag compensation techniques for the other games. So very similar games, comparable in terms of high speed, high interactivity between the players and so on, but latency influenced in a different way. So finally, what is then potential solution, or at least what would be a strategy to tackle the fact that we need to try to understand these different factors, and that's challenging. Well, it's one strategy there is to try to have more awareness around the ecological validity of study designs and of subjective experiments with users that are conducted. So that's something that we have been working on here at NTNU in collaboration with AGH in Poland, where we have tried to collect best practices from the literature and try to integrate these more. So in some cases, it's not so important that we have high ecological validity, so that when we are really sure that we are already focusing on the very important factors that influence the experience, then it may not be so important that we have a setup that is at all different levels, has very high ecological validity. But when we are not sure yet, and we still try to figure out what are the important factors, then we may need to have a design that has high ecological validity. And then in this work, we try to come with recommendations on how to take this into account. For example, again, coming back to the telesurgery, remote telesurgery example, I mean, it's very obvious that the task here would play an important role on the influence of latency on the QE. Or, for example, if you look at the dimension of participant recruitment, that it would be very different if one would have naive participants, naive testers, as opposed to actual experts who would actually conduct these procedures in real life. So there are a couple of recommendations there. And the question there is, of course, how does this picture now influence how we can model QE, this divide between QE and QS?
Good. From here, I take over. So as we have seen now, there's a lot of research also needed to find new QE models. We can use the existing ones also to derive a couple of interesting generic relationships between QE and QS. A couple of them are mentioned here on this slide. So for instance, we see here, I think a very important one, the so-called IQX hypothesis, which tells us there is a threshold, and until a certain threshold, a user does not react. And then we come into a very fast exponential decline. Yeah, in case of latencies increase, and it's really perceived by the user, and they get really annoyed about this until we come to a point where, in the end, it does not matter anymore if we get additional latency into the game. So what we also can do is we can use all these existing models, and it's already mentioned by Katrina, a lot of models have already been specified, subjective and also objective models by ITUT. There are also a couple of research papers out there, and they allow us then to be able to say what's now the impact of specific delay configurations and also bandwidth configurations on the quality of experience for certain applications. So here we have a couple of different applications. For instance, here, video on demand using Dash, or also live streaming using Dash. Of course, now here having different influence factors on the application control loop we have in adaptive live streaming, also then and how it reacts. But then, of course, manifests itself in the amount of stallings we have, the quality switches, and the overall video quality, which then results in different user-perceived quality or mean opinion scores. And we also see that we have, on the left-hand side, bandwidth-sensitive applications. On the right-hand side, we have more the delay-sensitive applications. And in the middle, with live dash, we have something which is in between. So we can assess all these things, and we can already then tune and optimize our technical systems on that. But of course, as already outlined, when it now comes to more applications with more stringent latency requirements, like for instance, telesurgery, tactile applications, I would say there we have limited QE models and a limited understanding so far. So at least to my understanding, nothing has been standardized yet. And we also see here a high impact on non-technical parameters like the context. In a telesurgery, it's completely different. Also, if we have haptic feedback there for a surgeon working, it's completely different to feedback which we get when, for instance, moving a drone around. We also see here a couple of requirements, what we are talking about. So haptic feedback in the area of 3 to 10 milliseconds. Here on the right-hand side, when it comes to the tactile internet, it's a bit more distinguished between operator to subject and subject to operator. And we're talking here about something like 1 to 10 milliseconds in a high dynamic environment, 10 to 100 milliseconds in a dynamic environment, and in the other way around, a bit different. So this brings me now to the final words of our talk. Do we understand latency? And For that, I also used the famous elephant. I would say somehow there are still many open challenges, but I think we are on a good way towards understanding it better and better. Also by taking also into consideration these additional factors like the context. So thanks for having us here today, and looking forward for additional interesting talks and also for feedback and of course questions.
Thank you very much, Thomas and Katrin. In the interest of time, I think we have to do the Q&A in writing and move on to the next speaker. Our next speaker is Marek Peszta from CDN 77. And Marek, please take the stage. Where you're still muted. I can see your slides.
Hello, is it better
now?
now?
I can hear you as well. Excellent.
Perfect. Thank you, Björn, for the introduction. So let me just fix it here. So my name is Marek, and I work at CDN 77, a global CDN provider. My today's talk is going to be about the challenges we need to overcome when we deliver HTTP low latency live streaming without compromising video quality and streaming stability. I will look at it from the CDN perspective, and it's a short overview of the optimization that we perform on the software and as a CDN provider on the physical CDN layer. Great, let's dive right into it. So we have heard already quite a number of definitions, and so what is the latency in context of streaming? And the ultimate question here is really how low we can actually go. So when we talk about latency, we usually use the term end-to-end latency, or maybe a more familiar term, glass-to-glass latency. In both cases, it's the time difference between what is happening in real life situation in front of the camera lens and what the end user sees on the screen, be it mobile, TV, or computer. However, it's not just the delay that we care about. And just as Bjorn yesterday referred to latency as the time to the first byte, another important live streaming metric is actually the first frame latency. So in other words, how quickly do you see the video when you hit the play button? And ideally, we want to measure it in milliseconds because you don't want to wait for it until seconds until it loads. So it's important not to sacrifice the first frame latency while we chase the overall glass-to-glass latency. So I will stick strictly to HTTP. So you can think of MPEG-Dash and HLS, although HLS is a bit more complex. So why do we have latency in the first place? Because HTTP protocol is not the limitation. We can achieve subsequent latency with just HTTP. However, the fun begins when we process the video and we transfer it over long distance and deliver it at scale. So I think many of you have seen similar diagram. So this is like a standard live streaming workflow diagram, and each unit adds a bit of the overall latency. So it begins with the ingest. It needs to be transcoded, packaged, and followed by delivery, and finally it ends with the video playback on the user side. Let's put it simply: if you don't care too much about latency, and each of those units can have a sufficient buffer, then this whole process is very fault resilient. So you can think of network buffer, read ahead buffer in the player, and so on. Nonetheless, when we try to reduce the buffer at each unit, suddenly the whole workflow becomes more sensitive to any data transfer and network instability. So that is the reason why we actually try to keep that 4-second window if the use case allows it, because it gives us some breathing space for a global delivery, last mile issues, network instabilities, and so on. So the challenges this brings are widely interconnected, and at the end of the day, it's all about these things: how quickly we are able to process the content, and how quickly we are able to pass it through the individual units in the live streaming diagram. So let me share a few ideas regarding transcoding, and then we will look at optimizing the software, and lastly at the physical layers. So first, let's focus on the transcoding part, whether the transcoding is actually outsourced to your CDN provider or whether it's done in-house. You will be facing the same big questions when dealing with latency. So these are just example questions, and you will need to think. When designing your setup, but they are all related to glass-to-glass latency. So do we use push or pull-based transcoding? In other words, do we automatically transcode every stream as it's ingested, or do we wait until the video is requested by a user? Do we sacrifice the video quality in the sake of low latency? And where does the video processing take place? Can we reduce the latency by moving the transcoding to edge, for example? So no simple answers to these questions, but they are all use case and of course cost dependent. So let's just review the difference between the push and pull transcoding. So during the push transcoding, we transcode every stream as it is ingested. So we have it ready. We might have it ready on the origin level before the user requests the video. So this is great in terms of first frame latency. And this is also beneficial when you have relatively low number of streams, because you can easily plan your transcoding capacity. On the other hand, in pull transcoding, which is employed quite frequently for user-generated content, you want to transcode only streams or qualities that are requested, because it makes perfect sense from the cost and resource planning perspective. If you can have a long tail of video content which may never actually be watched, and you want to utilize the transcoding capacity wisely. However, in the pull transcoding, you are losing the advantage of having the stream ready when requested and when requested by the first viewer, and this is impacting the first frame latency. So the trade-off between bitrate values, encoder load, and latency is unfortunately the video quality. So as mentioned earlier, it's all about how quickly we are able to process the stream and move it along the live streaming workflow. And when you try to squeeze the process of transcoding in, let's say, 20 milliseconds window, you're likely to drop some compression optimization, primarily look-ahead algorithms. And in other words, you are losing B frames because you simply don't have time to wait for the future frames. And finally, for transcoding, where do we put the processing stack? Can we reduce the latency if we move the video processing to the edge? In other words, closer to the end user? Well, possibly yes, but it's not the ultimate solution. It also depends where the ingest is, and if you need to transfer the original stream over long distance, you may save some bandwidth, but with global audience, you will end up with transcoding the same stream at multiple edge locations, and this is definitely not cost effective. So many questions, not simple answers, trade-offs, and we haven't even packaged a single segment. So let's look at what does the CDN play there. So as evident from the face of my colleague, there is a large pool of features but it all comes down to the ability to serve and store segments before they are actually created and cache them before they get requested by a client. So let's just look at how video segmentation works. We know that CMAF is a continuous stream that's broken down into small video segments. And in reality, they are actually small MP4 files, usually between 1 to 10 seconds in length, depending on what you want to achieve. So these video segments can be requested through both MPEG- and HLS manifest files. And one way of reducing latency is actually shortening the duration of these segments. It's a valid method, and from our own experience, we have, just by shortening the segment, you can get close to 5 seconds for glass-to-glass latency. For us, the segment is the smallest addressable unit. Each unique segment means a new request to origin. And by lowering the segment duration, this increases the number of segments and means more requests, and more round trips and more HTTP overhead. At the same time, every segment has to start with a keyframe. So with the segment, which is shorter, let's say 1 second, you might have to reduce your GOP size and end up with lower quality for a given bitrate. When working with completed segments only, you have to always wait for the segment until the segment is created before sending it to the client. And this waiting for the creation of the segment adds to the overall glass-to-glass latency. In fact, Damien from Broadpeak talked about my slide, about my next slide, which is about the HTTP chunk transfer. So instead, we rely on the ability to transfer the data to the next layer before a single segment is fully created. And we do this by breaking down the video segments into even smaller units. Let's call them chunks. And instead of waiting until the completion of a single segment, we pull and deliver chunks which can be as small as several milliseconds in duration. So from the HTTP perspective, when a request for an incomplete segment is received, instead of answering with 404 or waiting until the segment is completed, it's served partially as it's being created. And this actually results in kind of a hybrid of a file-based request response method and stream-based method, such as used in IPTV. However, this leads us to adjusting each unit in the workflow and teaching each unit to read and serve those incomplete files, those chunks. And most market-ready or standard storage solutions are not ready for that. They don't allow you to start uploading without knowing the total size or reading incomplete files for that matter. So you need to keep in mind that a custom origin implementation will be necessary, and it will be serving usually the data directly from the memory. And in regard to the caching infrastructure, we are moving the chunks across the caching layers. So regardless how many layers there are, the principle remains the same. As soon as the smallest playable unit is created, it's passed down to the next level. And this requires each layer to be able to cache these incomplete files using, for example, request coalescing, which is consolidating similar requests into a single request and optimizing resource utilization. And the real strength is when you combine the HTTP chunk transfer with data preload. So because of the knowledge of the next segment URL, we might use HTTP push to preload the segment before they are actually requested. So when we initiate data preload for a segment which is not even partially created, Instead of origin returning 404, which would be expected, it keeps the request open until the first chunk is created and passes it forward. And by the time a piece of video is requested by the end user, we should ideally have it created and cached as close as possible to the end user. And moving onto the caching infrastructure, CDN then ideally uses multiple caching layers, with the first caching layer located closest to the origin. And also, it's always a good practice to set up a redundant PNI with your CDN provider. This same idea applies to edge layers and their close proximity to the end user. And the idea here is really to eliminate the dependence on the public internet as much as possible. And it leads us also to the network infrastructure itself. Well, as a CDN provider, we are often guilty of sharing slides such as this and boasting about how many global POPs we have, and talking about our coverage, because it doesn't tell the whole story. Especially when we talk about low latency live streaming, the way we transfer the data between the origin and the CDN edge is equally important. In low latency streaming, the cache is inefficient. Yes, it helps to reduce the load to the origin, and yes, it helps to amplify and scale and deliver, but it does not save the performance or availability when there is a network issue on the path between the origin and the edge. So if you consider a VOD scenario where you have where your cache hit rate is, let's say 95%, if for whatever reason the cache fill breaks for just 10 seconds, for example, over 95% of your content would still be delivered from the cache. So, and at the end, the user wouldn't even notice it. But with less than 4 seconds between what is happening in real life and the playback, we don't have that luxury. So therefore, it's really crucial to have a reliable network which ensures a constant flow between the origin and the end user. In low latency streaming, even the slightest network instability between the source and the client impacts the performance and thus the user experience. So it's not just about how close you are to the end user, but how well you are able to connect the end user with the content. And this forces you to revisit your internal network and backbone redundancy, or how quickly you are able to identify a network issue and how quickly you are able to resolve it. And to sum it up, the technology to deliver HTTP low latency live streaming at scale is ready, and we do it, but it forces us to be super efficient with the data transfer to make up for the relative comfort that high latency gives us. And if you want, we can connect on LinkedIn. This is my QR code. And with that, I'd like to hand the word back to Björn.
Thank you very much, Marek. And again, in the interest of time, please, we'll do the Q&A in writing.
Of course.
And I will introduce our next speaker, Wim de Ketelaere, who is the CTO of Exentis, and who will be talking about L4S and low latency DOCSIS. So Wim, please take it away.
Okay, thank you, Björn.
We can hear you, and it looks like your slides are coming up. Very good.
You have them?
Yes, I can see them. Thank you.
Okay, thank you. So my talk, I will be a bit short on time, I think, will be about L4S and low latency DOCSIS, some insights from the lab that we've done here in Belgium again. Okay, that's me. I had to put this slide in for marketing, sorry for that. So First of all, it has already been explained a couple of times. What is this now? How is ELF-REST used in DOCSIS? Well, I've tried to summarize it on this slide. It's hard to beat the presentations of my predecessors here. But basically, looking at DOCSIS, we have a cable modem here on the left-hand side and a CMTS on the right-hand side, where from a downstream point of view, the CMTS transmits packets to certain cable modems, and these packets belong to a certain flow, okay, which has some aggregate characteristics, as for instance, maximum speed, maximum packet rate. Packets that come in and that are selected to be transmitted to a particular cable modem, in that scenario, have to go through a classifier, and the classifier selects to which of the two queues, a classic queue or latency queue, the packet will be put into, okay? By default, in DOCSIS latest versions, ELF-REST packets will be automatically put into the low latency queue. A classifier will be there. So we have two queues. In the low latency queue, the marking function, the ELF-REST marking function, the probability that a packet will be marked, that congestion has been experienced, is configurable. The RAM function, you can configure, okay, at the maximum, I want to have a latency of a certain amount of milliseconds. And before that, from a certain amount of milliseconds, I will already introduce marking based on a linear probability. So basically, if your buffer is 50% over there, the likelihood that a certain packet gets marked is about 50%. Okay. Other packets that are not put into the low latency queue are put into the classic queue. And then, as I explained before, we have this weighted scheduler that basically makes sure that none of the two queues can start. In DOCSIS, you can even configure the weight of these weighted schedulers, so you can play a bit with how much importance you give the low latency queue versus the classic queue. One additional aspect, which I think was not touched yet, is what would happen if you have an application, whatever it is, that's misbehaving. Because, of course, one important aspect of low latency ELF-REST is that applications for which the packets are marked, basically congestion experienced, please lower your rate. But if for whatever reason those applications do not listen, they don't adjust their rate, or maybe the classifier was put in there and it was not really for an ELF-REST aware application, it was just for DNS traffic or whatever you wanted to do, there is this aspect of queue protection. If at the moment the queue becomes too full, a queue protection will move some packets from the low latency queue, the most offending packets, to the classic queue to just protect basically the latency experienced in this low latency queue. Okay. Experiments in the lab have shown, of course, this queue protection can sometimes act a bit weird, I would say. If you're not careful, it can cause packet out of sequence behavior and all kind of stuff. So then, depending on the application that's responsible for that, you end up with potentially strange behavior. In the upstream, low latency DOCSIS does a couple of extra things in the upstream regarding to the scheduling, because of course in the upstream, the CMTS is the controller, the scheduler of all upstream transmissions, but still the cable modem performs exactly the same functions, but then of course in packets coming from the customer side to the operator side, to the upstream. But the same logic is applied. You can configure this RAM function, maximum latency, so a certain flow, from which latency on you start to mark packets. Queue protection, you can enable or disable this, exactly the same mechanism and this weighted scheduler. So what we've done now, we've basically done an experiment to just say, okay, if you take a CMTS and a cable modem, okay, it's a very simple setup, one cable modem, one CMTS, and on the first modem, you just send TCP, nothing special, cubic, okay, combined with, well, so you have TCP full stack. Okay? We'll do the retransmissions, everything. We'll respond to packet loss, everything, combined with a UDP flow. Okay, UDP flow in this case, I believe, was 64 packets per second over a classic flow. And a little bit to be fair, we've also enabled AQM. Okay, active queue management, I would say, should be enabled now these days anyway. Second setup, or second system, does exactly the same thing, but we enabled L4S. So the TCP stack was TCP proc L4S, okay? And on the UDP packets, we also enabled L4S. And of course, on the cable modem and the CMTS, we had everything configured to have low latency DOCSIS enabled, an aggregate service flow rate, and the queues configured for the ramping function, everything. And based on that, we just want to see what's now happening really. What's now the impact? Well, okay, those are the results, of course. Well, of course, first of all, we chosen the parameters a bit because you can select many, many parameters in a DOCSIS system. The goal was for TCP throughput, okay, to be kind of a little bit fair, say, we wanted to kind of achieve the same speed, and we did achieve the same speed, okay. Our rate was configured to be a maximum rate of about 200 megabits per second. And L4S, indeed, okay, as you can see, it nicely, and that's of course the big difference between an L4S, it kind of has some ramp up, yes, of course, but then it almost stayed flat just below this maximum speed of about 200 megabits per second. Cubic with the classic AQM, it ramped up, okay, got some speed, but then dropped down a bit, ramped up a bit, okay, and you had this sawtooth behavior. I mean, not that bad. It didn't drop to like 50 megabits per second or something like that, but still, of course, you can see there was some drawback. Now, from an average throughput point of view, the difference between the two is very small. If you, however, look at the latency, the one-way latency, okay, this is UDP packets down, coming from CMTS down to the cable modem, where we configured this latency target, okay, the maximum value here of the time in the buffer to 10 milliseconds, we nicely saw that the system was able to keep that latency nicely below 10 milliseconds, okay? So basically, the marking on the TCP packets, congestion marking on TCP packets, made sure that TCP proc stack was rate limiting itself enough that always that latency was low enough that basically the buffer was never full. In the classic system, okay, AQM with TCP cubic, also UDP flow, okay, one-way latency for UDP flow. Initially, it ramped up to even 30 milliseconds, which, let's be realistic, is still not that bad, but okay, significantly more than this 10 milliseconds. Then drop down, and then, of course, we can see that it kind of also, depending on the sawtooth we have in the TCP, it also has a big impact on the experience latency. At the moment that the TCP is going down, sending less aggressively, latency also goes down. At the moment that TCP is accelerating again, latency goes up until, of course, at the end. So what can we conclude from that? Okay, in the end, that's important. While achieving the same TCP throughput, you could say the same efficiency on the link, the maximum speed that was configured was 200 megabits per second. Okay, so you could not go higher. The L4S configuration did significantly lower by a factor of 3, 20 milliseconds, the latency in this system. Okay, even though you had a TCP session in parallel going on, TCP proc, of course, with the L4S UDP, the TCP was not killing latency on the UDP. With the classic TCP, if you just do that, depending on your AQM settings, of course, as well, it really comes down that latency rises up to, in this example, 30 milliseconds. I do like to stress, however, it has already been mentioned before, that in the end, L4S, to work correctly, it needs to be supported, well, by the endpoint, okay, the TCP stacks on the systems, okay, that's clear enough. But also this marking behavior, okay, that we have over here, this mechanism, okay, if everything's LFRS, I think we don't need the classic queue anymore, you could argue, but at least the marking mechanism needs to be implemented, supported on the device that is the weakest link. Now, in a scenario, an access network scenario, it might not always be the access network, the cable modem with the CMTS or the ONT or the OLT, but in Wi-Fi scenarios, for instance, of course, Wi-Fi with the speed varies very heavily on where you are with your tablet, smartphone, laptop, compared to the access point. Might be the access point who basically has to implement that LFRS marking, because if you're far away, you're at a speed with a very low rate, and then the queue will start building up in this Wi-Fi access point. Okay, and I think I did not go over time. So thank you very much. And well, also, if you have some more information, you can also email us at lfrs@exentis.com. Any questions, if we still have time?
Thank you very much, Wim. Yes, we do still have time.
But no questions.
In the Q&A tool, I don't see any questions at the moment. I did see a raised hand though, but yeah.
Okay, thank you.
Okay, thank you very much, Wim. So that brings us to our next speaker, who is Stefan Brückelmeier from MaxLinear. And he will be talking about minimizing latency in consumer gateways. So please, Stefan, take it away.
Okay, hi there. I'm talking about the latency stuff, and actually more like the working latency as discussed earlier in the gateway. So we are chipset manufacturers, so both for the cable as well as for fiber, Ethernet, and so on. So basically what we do is actually we do the stuff in hardware, so that you don't spend latency on basically processing that stuff in software. So what I prepared, if it moves on, is actually real life scenarios that we just did recently with some measurements together with operators. And I just took 3 examples. So basically, I will go through the mechanisms and techniques that we have inside the devices in order to what we all discussed about now the last 2 days, basically in certain aspects. And I will show basically certain use cases that might be surprising or not in terms of behavior and latency accumulation, PPPoE, asymmetric traffics, and what happens if your service rate is lower than the line rate. And last but not least, as a kind of a summary, quoting one of my customers, latency is the new currency, but I think is a very good slogan for the whole thing. So getting started, we have different means actually, and we think we really have to attach all of these means in order to have a good end-to-end service quality of experience overall. And it starts from the physical layers below, and here we have differences. The PON has different means than the cable HFC network. So each of them provides some stuff, and then basically it adds on top the physical layer on the WAN port, then the Wi-Fi. I think it was mentioned a couple of times that also saw some comments that Wi-Fi is not enough presented in this round. So maybe for the next round to add more on this one, because yes, I agree fully. Also on the Wi-Fi side and the migration from the Wi-Fi to the WAN, then basically doing AQM codel inside the SOC in hardware. Not to forget exapression and prioritization. I will show that just on my next slides as well. And last but not least, we just saw it, L4S, of course, helping, but it's an end-to-end. So we have it on the DOCSIS, but we haven't seen it yet on the traditional telco kind of providers really being deployed. Having said that, from an overall possibility perspective, let me take a very simple one. you have a gateway router, you go in with a 10 gig Cat7 cable, UDP, IPv4, keep it simple. And you have also 10 gigabit out. But you go into the network and the operator wants to have PoE. That adds actually 8 bytes, 8 bits to the packets. So your rate actually goes down a little bit. Instead of the 10 gigabits that you're pushing, you only get 9.9. Not a big deal. Well, actually, if you don't do anything, you add, and it's only 1 millisecond here, but you add a millisecond just because you're piling up stuff and not nice. So it's just one aspect. And if you then apply AQM Codel, you see, okay, it throws away stuff as needed. You avoid the drop tail and basically go down with the latency to 0.6. So halving or minus 60% of the overall latency by just doing this small thing. Again, it's not a lot, and you will see on the next one where there's bigger numbers coming. But the thing is, all of these things happen at the same time. So this thing happens at the same time as the other, at the same time as the other. So all of these things are adding up and making it, let's say, very intransparent in the end what's really happening. So just to make you aware, even small manipulations can have a bigger impact. And of course, all of that is done in hardware, and you have all the tubes and knobs that you need actually to fine tune that to have a good system handling. The next use case, maybe a bit more interesting, and I saw also some comments that fixed wireless might be not totally represented yet in these rounds. So one of they asked was actually, what happens in a scenario, and I took it because it's very asymmetric typically. So what happens in a very asymmetric network behavior? A lot of downstream. In this case, the fixed wireless was sent to 300 megabits per second in downstream and a 20 megabit upstream connectivity. And there was a target of having less than 5 milliseconds latency in this constellation. And so for this one, what we used is TCP throughput or TCP traffic. And you see on the left side here, that's just the targets. So 300 down, 20 up, 5 milliseconds each. And as mentioned by Jason from Comcast, it's typically it becomes interesting if you have various streams. So in this case, for example, there is another upstream going on. So the 20 megabits that really is making your upstream channel full. What happens then? So if you don't do anything special, so just as you normally would, your data rate really drops down for the downstream from 300 to, in this case, 93. The latency is super, no problem. So it was just basically throwing away the packets that could not be dealt with. But of course, this is not what we want, right? So you look into the patterns and say, yeah, we missed basically the TCPs. So the TCPs basically they're in the upstream direction were getting lost, and this is why in downstream the rate was reduced by the TCP stacks. So let's do an ACK prioritization and an ACK suppression, so minimize all this ACK kind of stuff to make sure the ACKs are really going through. Now, what's happening is the throughput is now perfect again, very close to the target, good. But man, what happened with the RTT? Really bad. So in this case, it really, without doing anything in this congested scenario, it skyrocketed nearly to 500 milliseconds in downstream. This is of course not acceptable. And when you then enable, in addition to the ACK suppression and prioritization, the AQM, now you get what you wanted: good throughput and also good delay, actually exactly meeting or nearly exactly meeting 5.5 milliseconds and 5 milliseconds on the latency. So just using one means like the AQM, not sufficient. Doing basically a combination of ACK suppression, prioritization, and the AQM, reaching the goal of having a good traffic, both fast as well as with the full throughput in such kind of a scenario where you have very asymmetric rates. And now you might say, I'm not having that often, fixed wireless, not my use case. But also imagine if you have a shared network like on a PON side, and there is a lot of upstream happening with the others, you share the network, it can even be dynamically happening that your upstream rate goes down. And then you would see exactly the same behavior in a PON or in a cable network where you share basically the network with the others, and you don't have a dedicated bandwidth for this. Good. And the third use case is basically if the service rate is smaller than the line rate. So in this, just a very simple example again, you use an Ethernet inside your home, you have your router, and then you go out you say, yes, I'm connected to an XGS PON, 10 gigabit network. But you only subscribe to 100 megabit. So again, you have much more traffic coming in, and very, very similar to what we saw before. You have, of course, a congestion case, just taking the comment from before. Yes, there is a congestion in the sense of the rates are not matching. And so again, here you would accumulate quite a lot of latency just because of this mismatching. So just thinking about, I have a big pipe, and even if the bursts go out with 10 gigabit, the sustained rate is much lower. So there's a shaping happening somewhere in this network to limit the whole thing to 100 megabit. So again, an AQM codel mechanism is helping quite significantly to reduce the latency for this traffic to the desired, like 5 milliseconds. In a nutshell or summary, it's important really to look at all of these different system aspects. So the WAN that I just showed here as simple examples, because it's way easier to measure and to display in such presentation, but also including the Wi-Fi, including the mesh, how these things go together. So having this kind of step-by-step inside the home network and then going out to the access network, really taking each of these portions into account. Use the mechanisms that are available, like AQM, like the AC, like the L4S, especially for asymmetric rates, especially for dynamic adaptations, where you really don't know what's happening. So I had this experience. I was just in summer in vacation, super fiber line, and man, everybody was apparently doing downstreaming while I was trying to do some gaming, and I got really, really bad stuff because my upstream rate was lower and it was higher than the downstream rate, and it really was confusing that gaming mechanism completely because it was not adapting to the dynamically changing asymmetric connection rates that were happening there. So doing this in hardware helps, and then basically what we are providing is a toolbox, and then basically partners, like also some of them here in these sessions, can build on top of it. So for operators really to get the best user experience out there and really have a good behavior. And of course, there is tons of different statistics, counters, whatever that we have access to. So if there is anything from you guys where you say, hey, I want to achieve this, or can you provide these kind of counters, whatever, in order to get a better overall experience, please contact me. There's a lot of ways actually of exposing additional information from inside the gateway that might be helpful for solving an end-to-end scenario from the service to the gateway up to the network. And yeah, with that one, I would open it up for questions.
Thank you very much, Stefan. We do have a question, and it's so Dave Todd is asking whether you've done a direct comparison with Cake. And I guess to follow that up, how do you do your ACK filtering or your ACK prioritization?
Okay, so Cake is definitely on the list of topics. It's a bit big, let's call it this way, for gateways. So looking at that at this point in time, how it could be implemented in a good manner. So of course we see the benefits there, but it's not so easily for an embedded system to integrate. Let's call it this way, without being able to disclose more at this point in time here in the open. And the second part of this question is, yeah, exopression built in for ATS. Yes, so not disagreeing that it's needed. As said, yes, fully agreed.
And just to follow up, so I guess the reason Cake is too complex for your use case is that you're running things at 10 gigabits. Is that correct?
Not so much, not so much from that one. It's more like the not so much the throughput, but really the complexity of the cake itself in terms of memory that it requires and resources overall. So work in progress.
All right. I think that other question is for Wim, actually.
That's probably more for Wim. So also it's basically goes pretty much also in line. So as the same mechanisms here are also used for DOCSIS. So there is of course the whole system behavior is really depending on how you configure linear queues. So there is hardware queues. You can by queue you can define what are your rates. How you want to handle it, which weight you want to give to it, and there might be actually reasons to do more than two queues. So on the last presentation, it was two queues. So it might be actually also make sense to use up to 4 queues, for example, in order to better separate the services and to better serve for the different needs of the different services.
All right. Okay, thank you very much, Stefan.
You're welcome.
So we are now in this slightly awkward position of having too much time on our hands. But I will still just jump to the next speaker. But Jeremy, feel free to extend your presentation if you want to.
Thank you very much, Björn. I should be able to get through it in time, especially with an early start. And it's fantastic to be able to follow Stefan very appropriately. Let me get my slides going here.
Right, let me introduce you first then. So Jeremy Austin, Senior Product Manager at Preseam, and they are building middle boxes for WISPs, which are wireless internet service providers that do various statistics, like data collection and also traffic shaping and other stuff. I'm sure Jeremy will get into all of the details.
Thanks very much, Björn. It's wonderful to be here.
We can now see your slides and I can hear you loud and clear. So
perfect.
Go ahead.
Thank you very much. I'm glad to be back for 2.0. My colleague Dan was in the previous webinar and I was delighted to fill in. I'm very excited about all this stuff. This is an illustrious company to be in as well. So yeah, I've been the senior product manager since 2020 at Adderlow Networks, working on our flagship product, Preseam. I'm in Anchorage, Alaska, so it's still dark outside. Most of the team is in Waterloo, Ontario. So I focus on analytics features, both in RF and on the latency and throughput side. We collect a lot of metrics, trillions of metrics a day. Today, I'm going to talk about some of the tools we use and things that we've learned from mining our data sets to assess how ISPs are doing. We got some good information from Stefan about kind of before and after of good queue management in fixed wireless. I'm going to have to mostly give you after because our customers are using the management tools that are available to us today with AQM. And of course, we're looking forward to seeing the results of L4S and all the advancements we've been hearing about over the past couple of days. So our data set tends to be operators who are doing a reasonably good, a reasonably responsible job of managing their latency and managing their network. So we've also observed that it's possible to keep latency low by just continuing to reduce overall throughput, leaving lots of headroom. But then if you're in that environment where you're providing artificial constraints to what your customers can do, then what is the metric that you should use to determine how good a job you are doing at meeting their needs, not just the latency side, but the throughput side. How much rate management is too much. So my title is a bit tongue in cheek. They're really, we still do need to manage latency. There's lots of work to be done, and we've been hearing some really good stuff about all the fantastic science that's work that's being done. A little bit about Preseam. We started in the fixed wireless world because, you know, when you combine in-home Wi-Fi with one or more additional hops of latency variable, capacity variable wireless in the last mile, you've got the same variable capacity problems that are present in shared fiber or on a cable physical plant, but it's more acute. You have the stacking up of behavior. So Preseam was started in 2017 by Adderlow Networks. Pretty affordable per subscriber cost as a middle box, as Bjorn said. We're well over 400 tier 2 and tier 3 ISPs globally. Our focus, of course, initially was on fixed wireless, which has the most acute problems, but we have a strong and growing fiber customer base as everybody hybridizes. And we're finding that fiber operators want the same level of visibility into the traffic that's going on in their network, and into that visibility of the customer experience, particularly as it is highly dependent on in-home Wi-Fi. So our quality of experience platform as a whole has a bunch of tools. Essentially, we like to measure, analyze those measurements, and help the operator improve their network, because very often there are things that the operator really can do in addition to just managing queues. So we capture very highly granular throughput and latency and loss stats for operators. We break that down by topology. I'll show you how that works in a minute. And then we also allow the operator to use AQM. In our case, it's FU-CODL with a little bit of stuff from Cake, but not the full stack of Cake. And then we also do access layer PHY analytics. That's what I came to Preseam to work on. So in addition to the network payload that we're measuring as it goes through as the traffic goes through our boxes. Where we sit in the network is generally, either pre-NAT or somewhere in the core if there's no NAT involved, and we measure the ISP's latency. So not the internet side, which is largely outside the ISP's control, other than with coarse movements via peering. We heard on the topic of cloud gaming yesterday how the application developer can choose latency based on the nearest data center from a latency perspective. But we've historically concentrated on measuring the parts of the network that tend to contribute the most controllable latency, that is what's under the ISP's control. They don't usually have control over the applications in any way. So that's the in-home Wi-Fi, that access layer, perhaps some middle mile, and distribution. So we measure TCP round trip time, and we use that as a proxy for overall connection latency. We find that it correlates very, very strongly with UDP latency when we do UDP tests. This, of course, continues all the way onto the in-home Wi-Fi. And then we map that latency onto the network topology to help the operator understand where the bottlenecks are. As Gavin said today, it's important to understand the latency of each hop and how much that's contributing to the overall quality of experience. So I'm going to show a few charts from our network report that we release for for operators or for anyone. It's free to everyone, and we'll talk very briefly about that at the end. Since this is just a really tiny little snippet, I'm just going to show you 3 slides here. Again, TCP round trip time is not the same thing as raw network latency or one-way latency. I noticed in the chat there's some discussion about the hard problem it is of actually measuring one-way latency. As the operator, the traffic providers, the content providers are doing, it seems at times, everything in their control to prevent us from being able to learn anything about that traffic that's going across our network. And there certainly are use cases where being able to understand how your network is doing really are in the consumer's benefit. So this isn't the same thing as one-way latency or ping, which includes the full round trip to the internet. There is extra noise, for example, in the ACK timers. So when we look at this chart here, where we're seeing the kind of the standard deviation and the distribution of packets here as a histogram over the last 3 years, you might be worried that 50 milliseconds seems really high. Well, you have to remember that includes in-home Wi-Fi. Any last mile congestion can add some latency compared to the 5th percentile. Like the minimum latency is going to be that propagation delay. And if we look on the right of the graph, samples over 200 milliseconds are binned in our histograms. And I've been pleased to see that we've currently dropped those packets that are kind of beyond the pale below 1% this year. This is not necessarily, some of this might be due to improvements in our algorithms, but this is largely due to operators actually doing a better job. This is showing you how an awareness and understanding of how latency impacts the customer experience can spur operators to actually do a better job for their customers, whether that's reducing congestion, managing oversubscription correctly, or improving the access layer. That's a huge part of it, is just simply improving it in the fixed wireless world. Improve technology as new generations of technology come out as well is really important. So those upper percentiles, like the 98th, 99th percentile, those are usually not under the control of AQM. Like no amount of AQM is really going to fix that. If it's something that is due to, I should say, no amount of core AQM is going to fix that. If it's something due to Wi-Fi congestion or Wi-Fi queuing, because not every home has good Wi-Fi queuing. In fact, I would say the majority do not yet have that. I know that's a mission of a lot of us here, is to get queuing at every pinch point in the stack. So those packets are really just not going to respond very well to central control. So we recommend that operators keep latency, this last hop latency, well below 125 milliseconds. That's approximately 2 standard deviations, what you're seeing here, as the internet itself adds some latency. And for real-time communications, you definitely want to be able to keep that below 150 milliseconds in total. So in general, we're very pleased with this slope. We've seen nearly a 10 millisecond drop in the median over the past 2 years, which we think is really fantastic. Next, this is a distribution of what we see for ISPs globally with download to upload ratios. Stefan touched on this briefly, where there's a point at which having insufficient upload capacity absolutely impacts the download availability. I have a local cable provider that happily will sell you a 2 gigabit down by 50 megabit up connection, and that 50 is more like 35, and it's really not adequate. You can experience many hundreds of milliseconds of queuing delay on that network because it isn't being well managed. I would much rather have a well managed 100 by 20 wireless connection with good latency. So we see this neat distribution around 10 to 1, trending toward 8 to 1. I would say that's very solid in terms of what users are actually going to need. So peak busy hour here, this is the metric in megabits on the X and Y axis. That is the average across all users, not the active users. So the active user will consume more than this here, kind of 3 to 5 megabits during the peak busy hour. But the average user, including inactive users, is really nicely tightly clustered with the normal distribution, both in downstream and upstream. So this is good for overall network capacity planning. You're planning your peering. It's not as good for planning your local access over subscription, because in those contexts, meeting the speed test, which the FCC is really pushing as a measurement of how well you're doing, meeting the speed test is the new target, unfortunately. And that means you're really going to have to pay more attention to what the active user is using during the peak busy hour. Most wireless networks here are not grossly oversubscribed. In most networks, the distribution is not linear. So there may be, a small percentage, 5 to 10% of the network that is significantly more congested than the rest of the network. I believe that's due to, because a few overloaded areas can dominate the latency results. I believe that's due to the nonlinear distribution of population. Of course, globally, we've got urban, we have rural, we have countries with centralized backbones. We have folks who can hit 3 IXPs. We have the gamut here. So for latency purposes, it's really not practical for wireless networks to be symmetric. The amount of essentially wasted airtime that would be in play if we were attempting to aim toward fully symmetric networks, that would be wonderful from a latency perspective, because it's that you want no queuing at all in the upstream. But I would expect to see demand rising, like in practical applications, closer to 5 to 1 and 2 to 1, both just due to market pressures, and also as there is more as higher modulations are available in fixed wireless, we'll be able to actually deliver plans that maybe have it's not going to be a gigabit down, but it may be tending more toward a 2 to 1. So I would expect to see some, 500 over 250, 400 over 200. I'd expect to see a lot of plans like that, and to have them be well managed. My last chart here is just total demand that we've been seeing, because one of the things we want to see is at what point is the user no longer experiencing significant delays overall? So once the latency is well managed, then if you're downloading a big file, at what point is the network really meeting the needs of the CDNs that are pushing to you and whatever task you're performing on the internet. So looking at these networks that are reasonably well managed from a latency perspective, what else drives if there's a shortfall? So we actually have quite a bit of fiber to sample, which would be those kind of north of 500 megabit plans. And I'm zooming in here on the bottom, under a gig here, under 500 megabits. I'm focusing on the bottom here, and because I want you to see the detail on the left-hand side here. Under 50 megabits, you'll notice that we see a very sharp fall off in the total amount of data that the user is able to download on a given month. This is due to congestion, right? This is due to the network, this plan not meeting their needs. So I just call it a limitation. The plan is actually limiting them. Above 50 megabits, though, we see very little constraint in the access network side. We do see that the access networks are able to deliver the speeds that the customer is asking for, but demand barely rises. If you look at the blue line on the bottom here, that's the 50th percentile. That's the median user here. Demand barely rises above 100. You see a very gentle slope. I think I measured it last year at something like had to quadruple the plan speed to double the usage. It was really a very gentle slope there. So most users aren't constrained by the access layer, the backhaul, or the upstream peering. But I would say if you want to take away from this, legacy plans, let's call them that, what they are, under 50 or 75 megabits, those are going to be an experience constraint. Even if it only takes 25 megabits for 4K streaming, you are going to be experiencing a constraint. Above 100 megabits, it's really hard to argue that most users aren't being met if their latency needs are being met. Higher upload capacity definitely drives lower latency, but it doesn't drive higher upload usage. And I just skipped that chart in the interest of time because I want to keep this right at 15 minutes. So our new wireless report showing 2023 is coming out in very early January. Please feel free to pick it up at preseam.com if you wish, and send me an email if you want to learn anything more about what we're doing over at Preseam.
Thank you very much, Jeremy. That's exactly 15 minutes. I'm afraid you misunderstood me though, because you're actually ahead of schedule now. But that's fine.
It's all good. I'll stop my share.
All right, very good. I believe our next speaker has to be promoted to a panelist first. Oh, there we go. All right. Hello, Luis. Yes, so our next speaker is Luis Miguel Contreras Murillo from Telefonica. And please, Luis, take it away.
So thank you, Bjorn. I will share my screen. So hopefully everything can go fine. Let's see.
Yeah, I can hear you well. And now your slides are showing as well. Excellent.
Okay, thanks so much. So, okay, so it's a pleasure to be here, and hopefully I will not get you too much tired, so I can take some time for introducing this initiative from Telefonica. So this is an ongoing initiative. Probably I will bring here more questions and answers, but I would like to share with you what we are doing in Telefonica with this idea of trying to let's say have or provide the better network from Telefonica for the low latency services for customers, basically. So I will present you an initiative that we are carrying over in the different Telefonica operations, and with the idea of characterizing the latency in the Telefonica and the different environments. I will go through that briefly in my presentation. So let me start then. So, okay, what is the context and the motivation? So, traditionally, in the operator network, the main driver for network planning was the throughput. So we have seen along the time the idea and the objective of providing better throughput, more bandwidth to the customers, and so on so far. But now, all of us it's clear for all of us, new services are appearing that are demanding low latency and jitter. So somehow both of them. So at least stability on the jitter and certainly low latency. And this depends on the kind of services we will comment later on in the rest of the slides. So the point is that together with the fact of the dimensioning the network according to the throughput and this permanent need of more and more bandwidth, we also need to start introducing the latency as the new driver for planning, right? So the point here for an operator like Telefónica is, okay, what is in our hands? What can we do in order to satisfy these new services and having this new dimension in mind, right? The point is that probably the bottlenecks in the network will never disappear. If we fix one bottleneck, another bottleneck will appear. So somehow we need to find ways of mitigating their effects, or at least understanding what could be the implications of having these bottlenecks in the network. And also very important to identify where these bottlenecks, let's say, could appear, or what are the parts, let's say, in the network that are more that could have where this bottleneck could appear more frequently, let's say. So the three goals that we stated at the time of starting this analysis was to identify the pain points. In such a way that we can define the actions for mitigating, for avoiding impacts, or for reducing the impacts at the end. Also to understand what is the best network that Telefónica can offer to the customers for these low latency services. So probably there will be a limit to up to the point that we can reach for offering these low latency services. So we need to understand that. So in such a way that we can, let's say, pass to our customers the message, okay, this is doable. Going further than that is not doable at all, and so. And then also important, because with measuring and getting insights of the network, we can understand what is happening, but also it's important to understand what could be the what-if scenarios. No, so at the time of taking decisions, for instance, for placing content or for placing services, what could be that kind of scenarios that we can reach, what we can improve, and so on and so forth. So there is also this modeling dimension that we would like to analyze and to exploit. So now I will present very briefly some contextual information that is probably common for all of us, but just for justifying, let's say, this analysis. So what is happening? Certainly, there are the emergency of these new services that are more time critical, let's say, right? So there are, this is probably common ground for all of us, the gaming services, the remote control video and audio, augmented reality, control of robots, and so on and so forth. So there are services that are somehow in the general wide area that would be probably the scope of operators like Telefónica. There could be others more local area oriented, where also operators like Telefónica could have some place. But probably what we are referring to is this, let's say, general wide area services, right? Because we have these end-to-end services with different access technologies, fixed access technology, mobile radio access technology, and so on and so forth. Here you can see in this information taken from a white paper from Ericsson, focusing on the gaming, for instance. Important thing to reflect here could be that even for a same kind of service that could be gaming, we could have even different experiences depending on the time of game, right? For a common application, in other words, for a common application, depending on the particularities of the application, we can even have different experiences for the service. This is important because what it's saying is that it's difficult to characterize an application per se. So there will be different flavors of the application. There will be different specificities of the application that probably are hard to control from an operator side, right? So we need somehow, what would be desirable would be to have some hints about the application behavior. So not only for the application itself, but the particularities in such a way that we could do something in the network if possible, right? Let me bring also some other detail of some other applications. This is coming from an initiative in Telefónica CTIO. I'm part of Telefónica CTIO, which is the corporate unit, the corporate technology unit. So we were doing some experiments with different companies and application providers for different kind of services, right? And also I put here together with some other values from the EPP. What I would like to comment respect these values that are probably also common ground for many of us is that it's also very difficult to characterize the services, right? So we can deal with some ideas of maximum latency. In some few cases, maybe some idea of here, but for sure, throughput, downlink, uplink. But in general, the point is that it's difficult to generalize and to characterize the different applications. So somehow, in summary, the problem is that we have no clear view of what is the problem we are facing, right? And these are the kind of applications that we can or that would be served in short term. Probably in long term there will be others that are even more will present more stringent requirements, more requirements that will be even more difficult to satisfy. But even for the ones that in short term, we don't have a full characterization of them, and this is difficult for the operator to trying to solve a problem that is not very well defined at this stage, right? So this is the contextual information about the services, what we are facing. But what is the exercise or the activity that we are trying to run in Telefonica? Well, we want to take a holistic approach. We want to analyze the different network segments, and here you can see not only access, fixed access, radio access, but also the aggregation, the backbone, the core, and the edge. Not only from the technological perspective, but also from the topological perspective, right? So to understand what would be the best place to place the contents. It's clear that the closer to the user, we will have better experience, but we cannot go, let's say, everything. We cannot move everything to the edge. So somehow we need to understand and to do a rational approach to this edge computing placement of services and so. We also want to take a look to the platforms, to the internet, and not I mean the bit here, but not highlighted. Also to understand what is the contribution of the devices. This is very important because the devices are out of control of the operators like Telefonica. So there is a piece of this cake that we have the control. There is another piece where we don't have the control at all. Okay, so this is the scope. And the implications of all these pieces are very well summarized from this slide that I borrowed from Francois and Finley. So every piece has impacts on the delay. At the end, delay and latency and jitter. So all of them are contributing somehow to the overall figure of the delay and jitter. Then the point that what we are trying to do is to understand what will be the different contributions from the different parts in such a way that we can derive from that some actions and to determine what will be the actions that have more impact on that overall figure, right? So this is why it's important to understand the contributions of the different parts, and this is why we are going in this holistic approach. So if with these ideas, we have set up a study group internal to Telefonica, where idea is to characterize the sources of delay or latency, the jitter, and trying to assign the optimal budget to understand what are the pieces that we can actionate, where our action will be more effective in terms of ensuring the best end-to-end latency. Define also the best strategies to measure latency in the network. So having a kind of common practices. I will show you later on that we are taking this approach in different operations in Telefonica. Telefonica has operations in different countries, so we are let's say multi-domestic network. So we have networks in Germany, in Spain, in UK, in Hispano America, in Brazil. So we want to understand the situation in all these geographies, and because the different nature of these geographies, because in some cases, like Brazil, for instance, Brazil is like a continent compared with the networks in Europe, with Spain or with Germany. In some cases, we are the incumbent operator. In some others, we are the challenger. In some countries, we offer only or mostly mobile services. In some others, we offer fixed and mobile. So we have different situations in the different operations. So we want to understand, to share practices between all of us in order to get the view of trying to derive common ground for all the operations in Telefonica. So we want to characterize the latency and jitter as well. We also want to analyze the engineering of the services. This is also an important point to address here. Is not everything is technology based. In some cases, the latency is also engineering based. To do a better plan of the services, do a better engineering of the services. Here, for instance, has room this idea of optimizing the placement of the services. And well, the final goal at the end is to define this low latency reference architecture. So we want to, from this analysis, to extract some guidelines, and then these guidelines to move these guidelines to the operations in order to have this low latency reference architecture. Having this set of recommendations, a kind of toolkit, in such a way that we can try to replicate in the different operations of Telefonica. No? This is the idea. And these recommendations will be technological, but not only technological as well. So methodologies for measurement, engineering rules for defining the services, best practices for using the parameters or SLAs or KPIs to look at, and so on and so forth. So, well, this is just to somehow also to reflect the point that there are different sources of latency and jitter. I took this just a reference from a paper from Brock Biscoe, sources of delay, structural delays, endpoint iteration, path delay, link capacity, and host. Somehow reinforce the message of that other slide that we have different sources, so it's difficult to just point out to some specific piece. We need to understand the bigger picture, and we need to understand the major contributors to the latency and jitter, right? So at the end, there are multiple directions to take, from planning to engineering, including the introduction of novel data planes. There were a number of presentations, for instance, referring to L4S, could be a direction. There could be also others. So what we want to understand is what is the proper direction, what is the proper thing that we need to do. Another circumstance that we deal with is the fact that generally in the standardization landscape, there are some standardization bodies that are the ones setting up the objectives of the services, like with 3EPP, for instance, clear for the mobile part and so. But there are other standardization bodies that are the ones defining the metrics, or even defining the benchmarking methodologies. So there is, in some cases, there is not an alignment at all between the ones that are setting the objectives, the ones that are setting the metrics, the ones that are setting the benchmark methodologies. So this is also relevant in the sense that we need to learn how to navigate across the different standardization bodies and derive from them the proper information to derive actions later on in the network. So, for instance, here we can refer to multi-axis computing. That is, okay, define some metrics for that, define some metrics for benchmarking, but at the end, these multi-axis computing capabilities are inserted in the overall delivery of the service, right? So, yeah, as said, we need to navigate. We need to also understand how consistent are these metrics. In some cases, they overlap. In some other cases, they don't overlap. In some cases, they define points of measurement that are common to other points of measurement from other standardization bodies, and so on and so forth. So we need also to have a consistent approach to all these myriad of alternatives and ideas and proposals for that. And also relevant is the fact that we are dealing with the OSI layer, right? So the OSI, the TCP/IP layer. So all the layers, all the segments as well, the access, the platforms, the edge, all of them present specific latency-related behaviors. So yeah, an objective of this analysis is to understand how to deal with these different views and how to make a consistent approach across all the chain. And then the quality metrics. I here added a couple of references. One from the report in BTAC, the latency explained report. Interesting in the sense that we need also to look at the proper metric and the proper values. We are dealing with average values, or we are dealing with quantiles, and so on and so forth. So also the purpose of this analysis is to define what is the proper metric to look at in such a way that we can spoke a common language, let's say, among all the operations of Telefonica, and trying to focus on the metrics that provide value. And in this sense, also interesting, because we are dealing with this end-to-end, is also to understand the behavior of the different metrics. How far we can compose the different metrics, how far from the information that we derive we can get valuable values for some specific parts of the network, or if we are measuring some different parts with different mechanisms, with different granularity even, how we can compose from that a metric that could be valuable end-to-end and then meaningful for the purposes of having this low latency network of reference that we are trying to build internally in Telefonica. Last but not least, the relationship then between the QoS, or the measurements that we can get from the network with the experience that the user could get. And here again, we face a myriad of standards and a myriad of options and a myriad of mechanisms or methodologies to look at in order to derive from this QoS the QoE. Also, we need to learn. We need to learn how to navigate across all these different options and start from these different alternatives. What would be the methodology of value that can provide us the proper way to follow, right? And this is a difficult exercise. And yeah, well, I borrow as well this slide from Francois and Lee, because it's very illustrative, the fact that, okay, measuring is not the last step. We need from that also to derive what will be the potential impacts to the customers, because the customer at the end doesn't care do not care about we have different segments, and so he wants to get an experience from his or her service, and he wants to get immediate and easy way of understanding what is happening in the network that I'm using for accessing whatever service. So that was about the measuring, and measuring, as said, somehow gives the view of what Telefonica is providing today. But what about if Telefonica wants to provide something in the future? What if I need to decide where to place some content, where to do something in order to improve the customer experience, or in order to improve the quality of service that I'm observing today? I need somehow to model the behavior of the network as well, based on these measurements that I'm getting. I put here a very silly example that could be the case of the transport network, where we could have some topology at IP level, but this topology at IP level is somehow connected, leveraging on optical network that is underneath. And this optical network is far between a point A and point B, is far from let's say, have a linear connectivity, a linear connection, right? So we need to deal with the geography. We need to deal from where this optical network is supported by fibers that do not follow a linear connectivity, and have some extra kilometers to spend in order to connect what in the IP layer seems to be just one hop. But one hop could be, or alternative hops for protection could be maybe 100 kilometers of difference. So we need also to model that fact, to model the behavior internal to the IP router, but also to model the behavior of the optical network. In the best case, we will have the information of these differences in terms of geographies, kilometers, and so. But in some other cases, we need to model that. So we also want to, as last step of this analysis, also to have some tools, let's say, in order to model in such a way that we can also, for those exercises that are kind of what if, or how I can improve the network, to have the sufficient information for doing that. So just as an example, this is a kind of toy tool that we are trying to develop, in this case with information of Telefonica in Spain, and trying to derive from the information that we are collecting and we are measuring, a kind of tool that could help us to say, as said, no, if I put service A in city A and the customer is in city B, what could be the impact, or what could be the best path to follow at the IP layer, and what could be the best path to use in the optical topology underneath, and so on and so forth. So we are doing this kind of exercises. In summary, and not taking more time from all of you. So we are taking some actions, this internal activity. We are working on a number of deliverables internal to Telefonica, so defining the low latency services, the services that we expect to consume the Telefonica network in short term, and maybe with a mid-term view, because otherwise the long-term view is rather speculative. So trying to understand what are the services that will demand the Telefonica network in short, mid-term, and trying to assess and benchmark the behavior of what we can provide nowadays. Okay, defining the observed quality of experience mechanisms that we are using today, and then an important deliverable, which is about the latency analysis per network segment. This is the point where we are focused now. We are working with the main operations in Telefonica, with Brazil, Germany, Spain, and also international carrier, the one using these submarine cables and linking essentially America with Europe, and so we are in here. I put a kind of zoom in order to show you what we are doing. We are analyzing all the different segments that they, at the beginning, the fixed access, the mobile access, the transport network, the core and edge, the impact of virtualization, and also, as far as we can, the impact of the terminals, both for the fixed domain and the mobile domain as well. And believe me that this is relevant and important, even though it's out of our control, but this is relevant for us to understand what could be the impact of this part, let's say, right? And for each of these segments, we are trying to understand what is the notion of latency and jitter in the network segment. In some cases, there are some overlaps between segments, so this is why it's important to understand what is the notion of latency jitter, what are also the points of measurement, also because we have this overlap, the methodology and techniques that of the measurement and the purpose of the measurement, what we try to get from that. Note that we have here different dimensions in the sense that we have the dimension of the different operations. We don't have a common approach in the different operations, and even in the same operation, we don't have a common approach on the different network segments. As you can imagine, in an operator, there are organizations, separated organizations for access, for core, for backbone, and so there is not a uniformity on how to address the same problem. So this is what we want to get from this analysis, is to put everything on, or all the people on the same table, and say, okay, what we are looking at, right? Also, the statistical parameters taking into consideration these average values, these quantiles, what we are looking at, and then important from all that exercise to identify the gaps. This would be the gaps and also the needs. No, that would be the final purpose as well of this exercise, to understand, okay, these are the values that we are getting, what we can do for improving that. Okay, what are the needs? What are not measuring today? What are the gaps that we do foresee or in the future for satisfying these services, and so far. With this analysis, we will go through the rest of the activity, essentially to define the guidelines for the reference architecture, to identify the gaps, to identify also the barriers, because, okay, we can just drop in here a kind of random example, no? Maybe one of the identified gaps could be, okay, we want to improve the experience in the radio, we need more spectrum. Okay, this could be a barrier because there is some regulation there, or even economical barrier, in the sense that, okay, probably we cannot acquire more spectrum, or this, these kind of things. So we want also to identify what could be the barriers that we, as Telefonica, we will face in order to go in this direction of the low latency reference network. We are working also with some vendors, equipment vendors and instrumentation vendors, to have this analysis, but from another angle, from the angle of the vendors, of the suppliers. So putting the suppliers facing the same problem as us, so in such a way that we can also get the views from them in order to enrich our decision at the end. No, it's not. I mean, we don't want to be Telefonica centric. We also are open to the external eyes in order to get also these views that will help us to enrich our final decision. And then important as well, the methodology. I said we are not following a common methodology, so probably could be now the time of setting up this common methodology, the common metrics to look at, and so on so far, in such a way that we can also benchmark and share experiences and extend these best practices across the different operations of Telefonica. And then there is some external action in different, you saw before in the slide, there are different SDOs touching these problems. So we need to navigate in this landscape and even contribute with the findings that we could have. So we are looking to, I highlighted here some of them, ITF, Roland Forum, the initiative in ITUT, which is modeling and so. It's important to look what is being standardized in order to set a common way of looking at the problem. We are also working with industrial associations. I highlighted here Telecom Infra Project, especially as well because I borrowed some presentations from some initiative in the Telecom Infra Project. It's important for the new services, the metaverse, and so to understand. I mean, to set a kind of common reference, because this is useful for us, but also will be useful for the customers. So to have a common understanding what they can expect. And then for in research and innovation, I highlighted here 3 of the projects we are participating related with latency, jitter, how to handle probably in more extreme situations, and also more looking forward. But it's important as well to understand what are the limits of the technology, and this is why we are also participating here. So with this, the conclusions by now, because I said at the beginning, these are more questions than answers. The point is that latency and jitter are emerging as new dimensions relevant for the process of network planning, network architecture at the end. So we need to add this new dimension to the previous one of the throughput, because the throughput will continue being a very relevant dimension of the network planning and architecture. There are multiple parameters and variables across the different network segments in impacting both latency and jitter. Not all the segments are necessarily under control of the operator. The clear cases are the devices, but we need to understand the impact of the devices, because in some cases we can realize that some huge effort in the operator side is somehow high because of the impact of the devices. So we need to understand as well where to put the proper effort, right? And this is why we want also to understand all that other part that is not on our side. And then with this is necessary to understand how is on the chain is impacting. So we need to get visibility, and the proper visibility, I would say. We need to be sure that the visibility that we are getting is the proper one. So we need to be sure that our understanding is the correct understanding, and with that to try to cure as much as we can the different implications, to define the actions. If we need to, as before, to get more spectrum, or if we need to define the number of splitters in the fixed access in a given manner, or if we need to define what could be the recommended edge location for the whatever content or whatever. So this is at the end the final purposes of this exercise. And here, as we saw, we highlighted, and in this seminar is quite informative in that respect. There are multiple fronts. There is the front of the technology that is clear. We need to leverage on the technologies that help us to get the best of our networks. But also there is some network or service engineering part that we cannot forget. So we need also to be smart at the time of planning, at the time of defining the service flows, at the time of defining the different points where we will deploy the service, and so on and so forth. And important, the methodology for measuring, the methodology for understanding the values, for raising the flag if there is some problem, and also methodology in the terms of modeling that could help us to anticipate to some problem, because, okay, as I said, no, we can get visibility of what we have today, but we need to infer how we could improve what we could have in the future. So this is an activity in progress in Telefonica, and I expect to provide more details maybe in a future webinar. By now, I would like simply to present what we are doing, and maybe collect feedback or questions, suggestions for the audience. And yeah, with this, I finish my speech. Thank you.
Thank you very much, Luis. This is very interesting. I'm looking forward to seeing where you go with this, because it's a very interesting project. There is a question. Brent Biscoff is asking whether you've done any testing latency impacts from mobile network slicing.
Well, for slicing in particular, we are not yet touching the part of the slicing. At the end, slicing will lay on top of all the infrastructure that we have today. So, but what I can do regarding the mobile part is where we are trying to define ways of measuring the mobile part. it's very difficult to characterize the mobile segment. The easy part is to leverage on the counters from the vendors and so, but the point is that the mobile part has, I mean, there is not a single pattern in the mobile part. Depends on the antennas that you have, depends on the number of users that they are attached to each base station, depends on the densification of each base station, and so on and so forth. So there are some characterizations, let's say, generic characterizations of modeling of the behavior on the radio part. We are trying to work in this case with different suppliers for having this characterization, but as I said, depends on the spectrum that you have, where the base station is in dense area, rural area. So there is no common pattern. We are trying to characterize some kind of prototype situations, so in such a way that we can, from that, derive somehow kind of general rules that we could later on expand or let's say assume as generic. Also important, in the case of the mobile part, we need to be notious that up to now the point was that the network planning was very focused on throughput, right? And all the planning of the mobile part was considering with the idea of improving the throughput. If we change now to the rule to improve the latency, then we will impact the throughput. And impacting the throughput or the coverage, at the end, the throughput is the coverage. This would imply that for offering the same coverage, we will need to increase, let's say, the number of sites. So this is a kind of game that we need to understand very well how to play with, because there could be implications if we try to improve the latency and at the same time not impacting the throughput, then there could be implications in the terms of planning. So by now, going to the question, we are working together with suppliers in order to understand what could be the way of defining a generic model, let's say, of delay in the access according to these parameters that I mentioned you before. The spectrum that we have, the number of users, the patterns is not the same in dense and rural areas, and so on and so forth. Hope that this clarifies.
Thank you very much. Yes, indeed. And with that, we are done with today's program. Thank you again very much, Luis. And I want to thank all of the speakers. Excellent talks today. If you are in the audience and did not catch all of the talks, they will be on YouTube once we are done with the whole event. And we will also attempt to share all of the slides that were presented today. And then I hope you will all join us again tomorrow. Dave Tott will kick us off at 4 p.m. Central European time. And then I hope to see everyone there. So thank you, everyone, and see you tomorrow.